Should we start allowing people to enter, or at what time do you think it's safe?
Yeah, that's fine. Yeah, okay, I'll let them all in.
It's safe.
Yeah, I'll just let. Yeah, that's fine. Yeah, okay, I'll let them all in. Good morning, everyone. Just to say we're going to be starting about 10 o'clock. If you could maybe just rename yourselves to make sure you've got your full name, that'd be useful, and maybe even your company affiliation in brackets afterwards, so we can see who we got online this morning. Speak to you in a few minutes when it gets to 10 o'clock.
Good morning, everybody. My name is Flor Sieperstein, and I want to welcome you to the Modeling and Simulation in Formulation meeting. That is an event organized by the Formulation Science and Technology Group and the Statistical Mechanics and Thermodynamics Group from the Royal Society of Chemistry, together with the Collaborative Computational Project on Computer Simulation of Condensed Phases, CCP5. We are really excited that you're joining us today. We have a very interesting program spanning from modeling physical properties of components that are relevant to formulations to prediction of formulation performance using machine learning methods. We have a nice balance of talks from industry and academia, and we are delighted to have the Elizabeth Colburn Memorial Lecture as part of this meeting. Elizabeth Colburn was a pioneer at ICI using modeling tools to aid in the formulation design. And this year, the Elizabeth Colburn Memorial Lecture will be delivered by Professor Panagiotta Angeli from UCL on the role of computational fluid dynamics in processing of complex fluids. But before we start, I have a few housekeeping announcements. Please make sure that you are muted and that your video is off unless you are talking. This meeting is being recorded, so please make sure that unless you are you're talking, you are muted and your video is off. Also, make sure that your Zoom name has your real name and your affiliation. That will help us know who is around and help others know who is in the meeting. Use the chat for questions, but also use the chat to introduce yourself, say which company are you coming from, and also you can use it for having some conversations with other attendants and do some networking. If you need a certificate of attendance, please send me a message directly from the chat during the meeting, and then I will make sure that you get a certificate of attendance. And I think these are all the housekeeping announcements for now, and I will let Professor Paola Carbone to chair the first session of this meeting.
Thank you very much, Flor. Welcome, everybody. So I'm Paola Carbone from the University of Manchester. And it's a big pleasure for me to introduce you the first speaker of session one, who is the winner of the 2022 Elizabeth Colburn Memorial Lecture, Professor Panagiotta Angeli. Professor Angeli will talk to us about the role of computational fluid dynamics in processing of complex fluids. So Professor Angeli, please, you can start to share your slides. We want to leave around 5-10 minutes questions at the end. So if you could finish, let's say around 10:40, we will have time for some questions.
Yeah, thank you. Can I start sharing? Okay?
I think so, yes, please.
So if we continue, fine. Right, I think you can see my screen.
That's correct.
Yeah, okay. Let me put it on full mode as well.
That's
excellent.
fantastic.
Thank you very much. Excellent.
Thank you.
Thanks a lot. And thank you very much for this invitation to deliver this 2022 Elizabeth Colburn Memorial Lecture. As the chair said, this talk is about the role of computational fluid dynamics in the processing of complex fluids. This is work we have been carrying out at UCL, the Department of Chemical Engineering, within the Thames Multiphase Group. So a few things about the motivation, what actually made us decide to work in this area. This grouping, I believe, is aware of the increasing level of sophistication in modern formulations that is actually driven by the changing customer demands, often for bespoke products as well, but also the need to move to sustainable materials. The companies need to deliver consistent product quality as well as meeting the customer expectations. But they face often uncertainties in the manufacturing processes driven by materials or local variations. So in this case, computational fluid dynamics has emerged as a tool to simulate the industrial operations in real conditions that can be used to design, but also to scale up the various processes. And it needs to be combined, though, with experiments at appropriate scales. So what I'm going to present to you is a number of case studies, where we have looked at the development and application of computational fluid dynamics tools for processes that involve complex formulations, complex fluids, and in particular, non-Newtonian fluids and dispersions. And the examples I will mention include both batch and continuous processes. What I will also argue during this talk is that we have realized that there needs to be a synergistic approach between the modeling and the experiments, not just for the validation of the computational tools, which is very important, but also because together they can help us build a better and a fundamental process knowledge. So I will start with some batch examples, batch mixing examples. Mixing is a very common process in industry. And a large part of what I'm going to show you is work that started with an EPSRC formulation grant, Coral, on the manufacturing of complex oral healthcare formulations. So what you see here is a typical process in the manufacturing of healthcare products, of toothpaste, for example, where the gel is prepared initially. It is then mixed with other liquid phases to modulate the rheology. And in the end, there may be additions, there may be more solid phases or other additives included in the mixture. And all this at various stages involves mixing in batch vessels. This is, again, a process quite common in healthcare industries. And one challenge that had been there was the fact that they wanted to include non-aqueous based formulations, where, again, the fluids encountered can have different or would have different properties. Let me see how I move now. Okay. To go like this. And so what we started doing is to develop the CFD, the computational tools, to model such complex mixing processes. Initially, we wanted to see what is the best way to include the fluid rheology, the liquids rheology of the rheology of non-Newtonian liquids in these CFD models. So the mixtures we were working with were carbopol gel in polyethylene glycol and glycerol mixtures. And these mixtures can have viscosities that depend, of course, on the shear rates, but also on the gel concentration and the temperature. So we did extensive experiments to develop the rheological model to characterize these mixtures, which we then implemented in our CFD model of a stirred vessel. To start with, we used a simple geometry. You see here a typical Russian turbine, just to make sure that we could capture this complex rheological mixture. So at the same time, the first level of let's say validation we did was to measure and to compute, to predict the power requirements in this vessel. And as you can see here, the measured values of the power number agreed very well with the CFD simulations. What, however, the CFD tool in this case allowed us to do is to see in more detail the flow field inside the vessel for different fluids. You hear a typical Newtonian fluid. These are all the very viscous formulations. The Reynolds numbers are very low, so we have laminar conditions. But you see here the typical pattern that you develop inside a stirred vessel with the two circulation zones. And what I show you here is the velocities, but in this case, when we have a mixture of the gel at a certain temperature, the gel is shear thinning. And as you can see, the velocities are really very much, the higher velocities are really very appear very close to the impeller, while the rest of the volume here appears to not be mixing very much. Of course, this is because a Russian turbine has been used in this case. To mix fluids like that, industry is using more complex impellers. And you see here a schematic of our lab version of a more complex impeller and vessel geometry that can be used for the mixing of such fluids. And we also tried to have a validation and a comparison between what we have in experiments and the models in a next level. So in this case, we try to obtain the velocity fields inside our inside our vessel and to compare with the CFD simulations. What we used to do that was a particle image velocimetry, where we put some tracers inside the very small particles inside the system, and we try to trace them with a camera and derive the velocity profiles. Of course, the PIV technique is very powerful, but there are many limitations. In the current setup you see here, we can obtain information on velocity fields just on one plane. It does require optical access to the system. And of course, if we need to obtain more whole volume information, we either need to use 3D PIV, which involves more cameras, or do a more complex experimental approach. Just a couple more things about PIV. We need to, what we do with PIV is we take images, two successive images at a very short time, and we try to cross-correlate the position of the particles in between these two images to derive the velocity profiles. The reason I'm mentioning that here is because when experiments and models, we really need to think, what do the experiments show us, what we measure, and what we get from the models. For example, when we do PIV, we need to, as I said, measure in two planes that are a little bit displaced from each other. So if our plane of interest, for example, is this one, it means that we have to make a measurement just a little bit before and a little bit after. This position can be 1 or 2 degrees difference. So, and by doing that, we actually get the average velocity on this plane. It's worth remembering that when we try to compare velocity profiles then from the measurements with the CFD simulations. We obtain this velocity field in our vessel. We're using PIV. And what I'll show you here is, just present everything, is that we compared these measurements with the CFD. That confirmed to us, as you can see, the agreement is very good. And that confirmed to us that the approach we use for the CFD, in this case, the CFD was a little bit more complex than the one I showed you before with the Russian turbine, because we also have the baffles at the side of the vessel. And of course, the geometry is much more complex of the impeller. But the agreement was very good. As you can see, the colors match. But also we looked at the velocities at this, let's say, plane here. The two velocity components that we could measure from PIV, the radial and the vertical one. So the agreement is very good, and that gave us confidence that the CFD tool could be used to obtain more information about the flow. And the type of information we get is what you see here. And so what I have plotted here is the isosurfaces of certain velocity magnitudes. And if we start from this corner here, where we have velocities that are 70% of the velocity of the tip of the impeller, high velocities, we see that these high velocities are really limited very close to the impeller. If we consider then lower velocities, 50% of the tip of the impeller, we see that these velocities can be obtained a little bit further away from the impeller. Even lower velocities, we go a little bit further into our vessel. But as you can see here, a large part of the vessel still has only very low velocities. That may mean something about the mixing, which is what we try to do next. So what we saw before is what is the motion of the fluids inside the impeller. It gives us an indication of how the mixing is going to progress, but it's not a real, it doesn't tell us how long will mixing take. So this is the next step of what we have been doing. And experimentally, to obtain mixing, we used a planar, laser-induced fluorescence, where in our vessel, we introduce a layer of our a fluorescent dye, rhodamine 6G in this case, and we measure the time it takes to fully mix into our system. The setup is quite similar to what we use with the PAV. Again, we need a camera, our laser to illuminate the flow, and we obtain images over time. And these are the results, again, from the experiments in this case. So that's what we get is in the beginning, the dye is all on the top, and then the impeller starts moving it downwards, and it takes so long to have this uniform concentration in the vessel. And if we want to quantify that, we can calculate this parameter, which is the difference of the concentration of average concentration at each point of the vessel compared to the final one, to the uniform one. So this will give us the time it takes to fully mix. The modeling mixing with CFD can be a little bit more challenging, and there are various approaches. One approach is to actually use we can model the concentration of a tracer inside CFD. Sometimes this approach suffers from numerical diffusion. If the numerical diffusion is comparable to the actual physical diffusion, then the results are not so clear. I'll show you some results later where we have used that approach. But what I'm showing you here is a different way of approaching the modeling of mixing, where what we did is that we actually modeled the flow field just using Fluent in this case, CFD software, and then we extracted the velocity field from Fluent into MATLAB, and we tried to see how these velocities would move massless particles inside our vessel. Let me see if that is playing. And these massless particles represent concentration of the dye. So if I leave it playing, you will see that after a while, the particles start mixing with the vessel. And we correlated this local particle concentration to dye, let's say a tracer concentration. And we could get the mixing in this case, which we can then compare with the results, the experimental results we had before. This is a nice technique. It does require lots of particles if we want to properly capture this concentration mixing. And some drawbacks it has is that if this works, if this tracer causes no changes of the local properties of the fluid. If, however, the fluid we mix, the liquid we mix causes local changes in viscosity, for example, then this approach may not be appropriate. So let me try to go to the next slide. Moving now from batch to continuous. This is the process we were looking before, a lot of mixing in stirred vessels. What we also tried to look is what happens if we move from the batch processing to a continuous processing using for the mixing inline static mixers. In that case, and within that project, we also looked at changing a little bit the actual process. So instead, for example, of having the gelation happening in the beginning and then mixing with a different fluid, the glycerol in that case, we saw what happens if we just mix the fluids from the beginning. And then once mixing is complete, we cause the gelation by a change in temperature. So moving from batch to continuous, we can argue that it leads to more compact systems. There is a better control of the residence time, so it might lead to shorter operating times. The process we chose involved lower viscosity fluids, so it is also more easy to mix. They're more easy to mix, and because it's more homogeneous, the transport phenomena are a bit faster and the temperatures are more homogeneous, it may mean that we can operate at lower temperatures. So we developed the CFD simulations to model mixing within, again, a continuous channel that had the static mixers. And this is the experimental setup for this configuration. In that case, experimentally, we looked at the mixing of two fluids that had a different color. So we could observe, again, with laser-induced fluorescence, what happens, how does the mixing evolve. And you see here some experimental results when we use two different types of mixers. That's a Kenix mixer. This is a bit more complex mixer. And these mixers work with the principle of splitting and recombining the fluid layers. So depending on how many elements you have, the fluids are split and then split again until these striations become thin enough for diffusion to take over and complete the mixing. For these studies, we used a Newtonian fluid as reference and also three different types of non-Newtonian fluids. One was a Boger fluid that had constant viscosity, and then two shear thinning fluids that had different shear thinningness and different also relaxation times. And we carried out experiments and CFD simulations. So what you can see here is CFD results of the mixing with one of these two mixers at different parts, let's say, of the mixer using different elements. So this is after the first element, the second, and so on. And we see this is the Newtonian case, and we see that what we expect is actually happening. The fluid is, the two fluids are split, recombined, and so on, until the mixing is better. Then we tried that with CFD with a different ratio of the phases. What we then try to do with CFD and experimentally is to see what happens when we put the shear thinning fluids. In this case, we, as I said, the fluids are viscous. We don't have, the flows are laminar. So what we saw is, perhaps not surprisingly, but what we saw is that the shear thinningness in this case did not play a role on the mixing. We still had fluids being split and recombined the same way as in the Newtonian cases, as you can see here. So actually, in this case, we did not have an effect of the shear thinningness on the mixing patterns. What we found out, though, is that once we started increasing the velocities and with the fluids that had also an elastic component, we then started observing other effects and instabilities. So when and you can see here some results for different Deborah numbers and at some point for different Mach numbers as well. So when the Deborah numbers were low, then we had a behavior, the same behavior as in Newtonian cases. However, when the Deborah number started increasing, as you can see, the solid part of the fluid took over in a way, and the fluid layers were not splitting as well. So you can see here that after two elements, we don't have the split you would expect in the case of the, let's say, the Newtonian case or the low Deborah number case. And quite interestingly, when we went to even higher velocities, and as you can see, or Mach numbers, elastic Mach numbers above 1, we started getting these instabilities. It's like as if the fluids are breathing. There are these fluctuations that we try to measure because we can see the concentration and we can see how these boundaries move. So we're doing a lot of this work, and for all the fluids that I mentioned in the beginning, we created this map. We have published this work, and so you can see more details there. But we created this map of the elastic number, which is the ratio of the elastic over the inertial forces, and the Mach number to see where in this map, in this within these numbers, the different, let's say, flow patterns occur. And we are in this Newtonian-like behavior when we are on the lower side of the elastic and the Mach numbers. And also we are moving on as the Mach number is increasing, then we start seeing the instability. So these sort of instabilities and the fluctuations appear in this region here. So the next thing we tried to investigate was what happens when solids are added inside fluids. And in this case, the modeling can be quite demanding. The approach we have been developing at the UCL is based on the mixture model, where we actually measure the rheology of the suspension, and then we implement it in CFD. Still, there need to be validations at various stages. And for validations, in this case, we use pressure drop and also the particle concentration. What I'll show you very briefly is some results where we compared these findings, these predictions of CFD to some literature data on what happens to the suspension that goes through a sudden expansion. This is the computational results. And what you can see here also is the comparison with these experiments from the literature, where the circulation length is compared for experiments and for modeling. So as you can see, the agreement is very good. We then took this approach, the mixture approach, to see if we could model the flows of dispersions, emulsions in pipes, in channels. This is the configuration we were considering. We had a static mix in this case to create the dispersion. And this is the information about the static mixer. And we could record, we could do all our, as I'm showing you here, we could do our laser-induced fluorescence and particle image velocimetry techniques to obtain in a pipe cross-section the concentration and the velocity profiles of the phases, which we would then compare with our CFD approaches. And what I have here is these findings, these results. These are the images of the flow. We have an organic and an aqueous phase. We have our tracer, the fluorescent tracer, inside our aqueous phase, and that's why it appears brighter. And we have two different velocities in the inlet, mixture velocities, and two different for the same organic phase volume fraction. So the lower velocity, you can see the drops are bigger, higher velocity, the drops are smaller, the mixing is a little bit better as well. So this is the image, that's what we see. Of course, we can read this image and we can get these experimental results. What we have in this top part is the concentration, the organic phase concentration, which is, as you can see from the images, higher on the top and very low at the bottom. The same in the when the velocity is higher. At the bottom here, we have the velocity profiles of the continuous phase. The continuous phase is mainly here, so we expect the velocity profiles to be, the velocities to be higher at the lower part of the pipe and lower at the top. So on top of these images, I also put the CFD simulations, the CFD results, and for the concentration and the velocity profiles. And as you can see, the agreement is pretty good, especially because this is quite a complex pattern. It's not homogeneously mixed, dispersed. There is this almost pure organic water aqueous phase on the bottom. And still, it is possible with this computation, with this CFD approach to model it. So let's say, recap some conclusions on what we have so far. I hope I have managed to show you that the numerical simulations can be very powerful tool for understanding and predicting the processing of complex formulations. But we do need in every step of developing a computational tool to have this synergy with experiments, not just for validation, but also because together both approaches will help us to have a better understanding and prediction of the flows. I would like, though, to conclude with a couple more slides, so this is not my final one, to mention some more recent approaches on machine learning and the use of machine learning technologies to improve these predictions. There are talks later on about machine learning, so there will be more about that later. But the way we have been using machine learning methodologies is twofold, is two ways, is twofold. So one can be to speed up the numerical simulations, and the other is to exploit very large, already existing databases. And I'll show you a case where we have used these approaches in formulations. So one, emulsions are used in many products these days, and microfluidics are widely used to produce drops that have small sizes, but also very narrow size distributions. Often in these cases, surfactants are used to control the for the stability of the emulsions, but also to control the size of the droplets. And of course, it's important to know what's this droplet size that can be produced from a microfluidic channel. So in this case, we tried to see if we could combine what we do with experiments and with CFD with machine learning approaches. So this is the setup we have been looking. It's a microfluidic channel that produces drops. And you can see here some experimental results for different concentrations of surfactant, no surfactant, and two different concentrations. And that's, again, velocity profiles, velocity fields inside the droplets. And as you can see, the surfactant does have an effect on the velocities. We lose the circulation pattern we have here as the velocity, as the concentration of the surfactant increases, and this would affect the drop size. So within our current EPSRC program grant Premier, we try to combine physics-based approaches, which is the experiments or the CFD simulations, with data-driven approaches based on existence and availability of data to provide predictions and quantify their uncertainty for multi-phase systems, for complex systems. So what we did then, and here are some results from this work, is that we used initially all the experimental data we had to derive a model for predicting the drop size in microfluidic devices in the presence of surfactants. And this is a model we have quantified these parameters here. We then used a very large database that we had available on drop formation and machine learning tools to, again, have a prediction of the drop size. And you can see here, how does this prediction with two different machine learning approaches compares with experimental data. This is actually a more easy approach, can be done within MATLAB. This is a more sophisticated one from our colleagues in Data Science Institute at Imperial. And yeah, as you can see, we can have pretty good predictions. For us, this is more of a demonstration tool, but we plan to expand it to cover different microfluidic channel sizes, a larger database of experiments as well, and surfactants. So with that, I would like to thank, first of all, my colleague, Dr. Luca Mazzei, that we've been working together on the CFD tools for the simulations I've showed you, and many of our researchers that have contributed to the experiments, the simulations, the slides I've just showed you. Some of them already in academic positions in other parts of the world, or in UK and abroad. And of course, our sponsors, EPSRC for a lot of help through some big grants and smaller ones, and the EU, and some of the companies that have contributed via studentships and case studies to what I showed you. And thank you very much for your attention.
Thank you very much, Panagiotta. So for the very interesting talk. There are actually a few questions. I'm going to read them from the chat. So the first question is from Philip Gill, one of the organizers. And the question is, what experimental data do you find the hardest to acquire to validate your modeling?
It can be many, and of course, if you need the degree of detail that I showed in some cases, for example, velocity fields or concentration profiles, these can be easy and hard to obtain. So, for example, in techniques like that, or when we have here it's more easy perhaps, but when we have the vessels. So this can be perhaps not so tricky to obtain, but optical access, which can be a little bit demanding. It's more demanding if we want to get more whole volume information, because in that case, we either have to use, for example, for PAV, 3D PAV, that involves more cameras. We lose a little bit on the resolution, the spatial resolution, if we do that. Another approach we used, because the spatial resolution, I haven't shown you results on that one here, is to repeat the experiment, but at different, let's say, slices, and then combine this data. And of course, this is pretty demanding. And because you have to match to see that then you compare the right vectors in the right slices and so on. And all these techniques, these particular techniques work with good optical access. And that's why it's there is a certain level where experiments and modeling can be directly compared. But then, of course, we can do more things with the modeling once we have established this, we have validated and we are confident on the results.
Thank you.
Having said that, there are other experimental techniques as well, and I'm sure people in the audience may have been trying them. There are tomographic systems, X-ray systems. We've been playing a lot with acoustic and ultrasound techniques lately. Again, very powerful tools, but you need the right level of validation to trust the results.
Okay, thank you. The second question is from Flor Sipperstein. Thank you for the very interesting talk. What are the key elements from the non-Newtonian rheology that are needed to have an accurate description in CFD simulations? How important is the microscopic description of the system?
That's very tricky, and actually it does depend on how complicated your simulations can be. So what I showed you here is simulations with using Fluent, where we have not been including the elastic components. So the shear thinning is easy to include. We have been trying, and my colleague Dr. Luca Mazzei is working on that, and we have a student to model in open foam, a lot to introduce, because you can introduce the, let's say, the polymer, some polymer models to try to also be able to simulate elastic components. But of course, the simulations get more tricky. And again, if we want to consider more than one phase is present, for example, particles in suspensions in viscoelastic media.
Yeah.
So what we found in this case, just to say one more thing, is that this it seems pretty simple, but it was actually in this case quite important to get this rheology quite correct, to have a very good prediction between the CFD, as I show here, and the experiments. So the actual rheology, although we didn't include any elastic components, was the shear thinning behavior, and the change with the temperature and the concentration was important to completely capture, to have a very accurate CFD.
Okay, The last question is from S.J. Anthony from the University of Leeds. I wonder whether you use PIV in the case of suspensions, especially when the particle concentration is relatively high. Thank you.
Right, we have done, again, I didn't show it here because we don't have the simulations. I was trying to have the focus on the parts where we have actually compared. We have used PIV and LIF in suspensions of a few percent volume fraction. Once you increase your suspension by matching refractive index of the solids, the fluids, and so on. I think we managed to get up to 5, maybe a bit higher percent. We've published some of this work, but then beyond that, of course, things become more tricky. You can go a bit higher if you are very careful. It depends also on the size of the particles. If the particles are a bit bigger, then it's more easy to increase the concentration. If the particles get very small, then it is quite demanding. It's more difficult. And that's why other techniques might be, it's worth considering other techniques as well.
There is another question, which I think you just answered, which is about, thank you very much for the wonderful talk. In case of suspensions, how high particle volume fraction could you simulate numerically also in your experiments?
So what we've done here, this is the mixture approach. And there is, I'm just trying to go here. This is a mixture of the mixture approach. And if I show you even these results here, we can, I will let my colleagues, Rashid and Luca, to comment more on the actual details of developing the safety model. But as you can see here, we can get high concentrations, and the same with this case where we have particle suspensions. But this is the mixture model. And there are certain limitations, let's say certain considerations. If you try to do individual particles, then then it becomes very demanding. And then, of course, you have to have a trade-off on how much you can do and how long you can wait.
Okay, maybe we have a very quick question about your machine learning approach, very interesting as well. So considering that some of these products are quite impure, so they contain a lot of impurities, do you find so that therefore the distribution of the data is very large? Do you think that this could be a problem when you try to, because basically fitting your data with the machine learning or any the kind of numerical methods within the machine learning tools?
This is actually learning for us as well. And that's why we used this system here, because over the years we had quite a few experimental data using, these results I show you here are from 3 different surfactants, concentrations that go below and above CMC, but using a very specific geometry. So, and that's why it was a great learning experience within the program Grand Premier to work experimentally, CFD modelers and data people, machine learning people, and see, to try to have a common language. So, and for us, this is an indication. You could argue this is not the most difficult case to model. We had a model that we had from experiments, based on experiments and on CFD simulations, combining the data. So it was not a case where we're actually looking for a model, but it was a good case to study. And in that case, combining all this data, and there was a lot of discussion among the team, within the team, on what we want to predict, which data do we include in our database, because you have to have nice data sets. While experimentally, sometimes you have the drop size, sometimes you have the drop frequency, sometimes you don't measure one aspect, the same with CFD. So it was quite a cumbersome work, I would say, to have this database. But once it was there, having the fluids that we had in the labs, which may or may not have had impurities, but that's why I mentioned we had quite a lot of surfactant concentrations, which perhaps is a little bit like the impurities. then we were able to develop these models. And there is in every one of those, there would be the, we used the model or the data as the correct, this is the answer. So this is differences from the correct, let's say, value. Yeah, the predictions were very good. And of course, we had a big enough database to have a large number of data for developing the model and then some for testing it. And the idea is that we now continue with this one. And the more surfactants we add, another thing we would like to do is to include different geometries as well. So we have a model that it's not just for one particular microfluidic inlet, but for a number of them, can predict drop size in the microchannels.
Okay, thank you very much. So there are no other questions. We are also perfect on time. So thank you very much again, Professor Angeli. We can't clap, but I'm sure everybody is clapping at home. And we can move on to the next speaker, who is Alessandro Patti, a former colleague of ours. So it's a big pleasure for me to introduce you to him, but now at the University of Granada in the Department of Applied Physics.
Okay, here I am.
Fantastic.
Hello, Paula. Thank you very much for your introduction. So, and good morning, everyone. And thanks, of course, to all the organizers for inviting me at this online event. I'm trying to get rid of. Okay, so in my talk, I will try to clarify to what extent we can use molecular simulation and relatively simple models to understand the behavior of polymer nanocomposites at very small scale. And also, we'll try to understand whether this behavior at small scales can be somehow linked to the behavior of polymer nanocomposite at large scale, so to the macroscopic response of polymer nanocomposites. Polymer nanocomposites are hybrid materials consisting of a polymer incorporating nanoparticles, and these nanoparticles can be spherical or can be anisotropic. And when we incorporate nanoparticles in the polymer matrix, we create a contact area, an interface between the polymer chains and nanoparticles. And this interface is very important because it is the location where the interactions between polymers and nanoparticle are established. And these interactions are crucial to determine the final macroscopic behavior of the material. So the aim is to maximize this contact area by, of course, maximizing the surface to volume ratio of the nanoparticle, which goes with the inverse of the characteristic length of nanoparticles. Polymer nanocomposites, you might already know, it's find application in a wide range of market segments whose annual growth rate is expected to achieve roughly $27 billion by the end of 2028. So it's a market in expansion. Why are these materials so important? Well, because by adding just a few percent in weight of nanoparticles, we are able to potentially improve a very wide range of properties, including mechanical resistance, thermal or chemical resistance. We can improve barrier properties against the gas permeation, and so provide additional protection against corrosion. However, achieving this property is not really trivial because nanoparticles tend to phase separate in the polymer matrix. And why? Because by doing so, the polymer chains would have additional free volume, so their entropy would increase, which means that the free energy of the system would decrease and make definitely this configuration more thermodynamically favorable. So, of course, this is not a situation that we would like to see. Why? Well, because the interface of contact between polymer chains and nanoparticles, where interactions are established, it would be very low. And also because this spot here might be a potential source of mechanical stress for the final material. So what can we do? One option is to modify the surface of nanoparticles so that their interactions with polymer chains will be made stronger, and the distribution in the matrix might be more homogeneous. But we can also work with other factors, or elements. We can work with the size of nanoparticles, their size distribution. We can work with the chain conformation. What would happen if chains were stiffer rather than flexible? But what would happen if we modified the architecture of the polymers so that we can create a nice background ordering where specifically designed nanoparticle with specific interaction might locate and might perhaps orient if they are anisotropic? So these are the questions that I will try to address during the talk. And let's see if we can find a nice answers. So the first case study is about the dispersion of polydispersed, size-dispersed nanoparticles in a melt of flexible chains. The model that we are using, as I already anticipated at the beginning, is relatively simple. It's a coarse-grained model where chains are depicted as a linear sequence of beads, and each bead is, say, representing a number of methyl groups, between 3 and 4 methyl groups. Nanoparticles have an inner hard spherical core surrounded by a soft corona, whose thickness is equal to half of the chain bead diameter. We have nanoparticles in this system of different size. They all spherical, but they have different size, and the size distribution is set by a log normal distribution. This log normal distribution has been modified to avoid the presence of unrealistically small nanoparticles. So nanoparticle whose size is smaller than the chain bead diameter. So we cut this area off and redistributed across all the log normal distribution profile. The force field is basically taken from the Kramer and Gress model for pristine polymers. We kept the essence of that model, but we had to modify it a bit because the Kramer and Gress model was generated for pure polymers. And of course, we have nanoparticles here, but we are keeping the most important elements. So the interactions between pairs of polymer beads are described by purely repulsive potential, by WCA potential in red here. And also WCA potential is used to describe the mutual interactions between nanoparticles. However, we are introducing an element of attractions between nanoparticles and polymer chains using a Lennard-Jones potential that is attractive in some range of distances. The bonded interactions are described by a combination of the Finney potential that you see here, plus the Lennard-Jones potential. This sum gives rise to this black line here, black curve, which has a minimum at roughly 1 times sigma m. So basically, this combination prevents polymer chains from crossing each other. The simulations, we are using 2 steps. The first step is using Monte Carlo simulation to create an original suitable configuration that we then use in molecular dynamics to further equilibrate the system. We first thermalize and then equilibrate it further. And finally, we use molecular dynamic simulation in the canonical ensemble to produce our time trajectories. When time comes to study the transport properties, the shear viscosity, then we use the reversible non-equilibrium molecular dynamics technique that is based on the Mueller-Plate algorithm. I just want to stress that regardless the size dispersity and the average diameter of nanoparticles, we always have the same volume fraction in the system, which is 5%. So we first look at the space distribution of nanoparticles in the polymer matrix. We have here 4 different frames where we report the radial distribution function of different set of systems. The difference between A, B, C, and D frames are in the average diameter of the nanoparticles from 6 times sigma up down to 2 times sigma. And within each frame, we see different curves that refer to different polydispersity index. So what we can see here is that the peak of the distribution is at roughly 2.2 sigma. So we conclude that there is enough space for polymer chains to intercalate between particles, which is exactly what we would like to see. We don't want to see clustering of nanoparticles. However, if you look at the frame C and D, you will see that there is a no-zero probability of observing shorter interparticle distances. And so that means that in these regions here, polymer chains might not be able to intercalate between particles, and clustering can be actually observed. This is especially detected when we go to this sort of unrealistically small nanoparticles. The dashed line refers to nanoparticles of size 1, so as big or as small, if you want, as the polymer chain bit. So in this extreme case, we have significant clustering. What happens to the mobility of nanoparticles in the matrix? To answer this question, we look at the diffusion coefficient of nanoparticle as a function of the average diameter of nanoparticles, here normalized with the radius of gyration of the polymer chain, and we also look at the effect of size dispersity. Simulations are symbols, while the dashed lines that you see here and there are the theoretical predictions based on the application of the Stokes-Einstein equation that you might not recognize because we modified it to include the effect of size dispersity through the use of the log normal distribution. So what we can say is, first of all, that the diffusion coefficient decreases with increasing the size of nanoparticle, which is an expected result. We know that the larger the particle is, the slower it will move in a medium. That was known. What was less clear was the effect of size dispersity. What we see is that by increasing size dispersity from 0 to up to 20%, the mobility of nanoparticles increase. And this is also predicted by theory. Now, the quantitative agreement with theory is not excellent, but we need to remember that the Stokes-Einstein equation is not taking into account the characteristic length of the medium. He assumed the medium to be continuous, while we know that we have a polymer here with a specific characteristic length. So when we choose a different theoretical model that does incorporate the effect of radius of gyration, then the agreement, the quantitative agreement with theory increases. So as you can see in here and in here. So what happens when we look at the mobility of chain bits? And this is quite interesting because what we see is that when we plot the diffusion coefficient of chain bits, here normalized by the same diffusion coefficient in a pure polymer melt, versus the interparticle distance, so the distance between the surface of nanoparticle, we see that all the diffusion coefficient of all systems we studied at different average nanoparticle diameter and different polydispersity collapse all on the same master curve. So there is a sort of universal behavior. This is quite also interesting because it is in very good qualitative agreement with experimental observation in the group of Russell Composto in the States. They studied polystyrene incorporating silica nanoparticle of different sizes and different size dispersity. So you see here that they plot the same diffusion coefficient versus the interparticle distance, which has been theoretically predicted as to be a function of the volume fraction of the system, which is the same, as I said at the beginning, for all our system, size dispersity, and average size of the nanoparticles. So this is interesting because if we plotted the diffusion coefficient of our polymer chain bits versus the size of the nanoparticle diameter, we might not see this universal behavior that we see if we choose the right parameter to analyze the results. Now the question is, do we see such a universal behavior only at this particle scale, or do we see also something similar when we look at the macroscopic behavior of polymer? So to answer that question, we wanted to calculate one very important property, the shear viscosity, to calculate the shear viscosity. Then we extrapolated the value of the shear viscosity for all systems studied as small shear rates and obtained the zero shear viscosity. We plot the zero shear viscosity here as a function of the specific interface area that is defined here, which is basically the area, the contact area in between the nanoparticles and the polymer chains. So again, you see here that this surface area, this interface area, depends on the volume fraction, constant in all our system, but also on the average diameter and size dispersity of nanoparticles. So what do we see? We see that when we increase the size of nanoparticles from 1 up to 10, and we cross a number of polydispersity and different average diameter, this curve converges to what theoretically is predicted to be the viscosity of micron-sized fillers. So fillers that are, of course, larger than our nanoparticles, and whose viscosity is predicted to be a function of the volume fraction only. So there is a quite nice agreement between this limiting theoretical prediction and our simulation result. So this is the first case study where we manipulated the size and the size dispersity of nanoparticles. But what if we change perspective and we want to understand how the conformation of polymer chains affect structural, dynamical, and transport properties of a polymer nanocomposite? So what we did was to increase the stiffness of chain up to observing a transition from an isotropic phase where chains are completely randomly oriented, and a nematic liquid crystal phase where chains are oriented along a common direction that we call nematic director. The colors here of the chains is just different to show you that how chains are oriented, but there is no difference between them of any sort. The model that we are using is exactly the same as the one I introduced before. The only difference is that we are now keeping constant the nanoparticle diameter. So we have a monodispersed system. The size of this nanoparticle, the diameter of this nanoparticle is 3 times the chain width, sigma. And we are also adding an additional element in the force field given by this bending potential that measure the degree of stiffness of chains through this constant kappa theta. We also have 4 different sets of interactions. So system A is the one where the interactions between nanoparticles and polymer chains are purely repulsive, while system B, C, and D, the interactions are gradually more attractive, from 1 times epsilon, the unit energy of the system, up to 10 times. So the first impact of this stiffness can be observed in the conformation of polymer chains, and that can be quantified by computing the radius of gyration and the end-to-end distance. You see here that by gradually increasing the chain stiffness, we see an increase of the radius of gyration and end-to-end distance up to a plateau that is more or less achieved at value of kappa theta that are at least equal to 10. So what happened between, say, kappa theta lower than 10 and larger than 10? Well, the order of chains increases. We measure this order by computing the nematic order parameter that is obtained by diagonalization of this tensor here, and where R1 are basically the unit vector that identify the direction of chains. Basically, they are defined joining the extreme, the endings of the chains. Of course, in an isotropic phase, where chains are completely flexible, this vectors, the pitch of this vector is meaningless, but then it acquires a very important, relevant, they become important when we go to a nematic liquid crystal phase. So the nematic order parameter increases from basically 0 in the isotropic phase up to 0.9 in the nematic liquid crystal phase. So how this affects the mobility of chains? So you see here that if we plot the diffusion coefficient as a function of the chain stiffness, we see that for the purely repulsive system and the other attractive system, the mobility of nanoparticles decreases with chain stiffness increasing. This effect is less evident when the interactions between the two species are particularly strong. And this is somehow expected because in this case, the interaction is so strong that the movement of nanoparticles is really hampered. Now, because we have an nematic phase, it makes sense to ask ourselves, does the anisotropic in structure affect also the dynamics? Do we see an anisotropy also in the dynamics of nanoparticle, in the mobility of nanoparticle? So what we did was to compute the diffusion coefficient in the direction of the nematic director, in the direction of the alignment of chains, and also in planes perpendicular to this nematic director. We did this for this first system and as a function of chain stiffness. Of course, the two diffusion coefficients are the same when we have an isotropic phase, but they then become different, in some cases quite different, when a nematic phase is observed, with the diffusion coefficient in the parallel direction larger than the diffusion coefficient in the perpendicular direction. We believe that the polymer chains are creating, the alignment of polymer chain is creating a sort of preferential path for the particles to move through. Now, is this anisotropy also affecting the response at larger scales of the material? Well, the answer is yes, as we can see when we compute the zero shear viscosity. You can easily imagine that when we have an isotropic phase, it doesn't really make any difference the direction we choose to apply a shear. But that difference is crucial when we have a nematic phase. So in this case, the resistance of the system to flow becomes very large when we apply a shear in the direction perpendicular to the nematic director. And the zero shear viscosity increases with increasing chain stiffness. The other two possible directions that we have represented here do not show any significant difference between them. It's also not a relevant difference with what we observe in the isotropic phase. So the last piece of talk is about how we saw how what's the effect of changing the geometry of nanoparticles. We saw the effect of changing the conformation of polymer chains. What if now we look at the architecture of the polymer? And what if we now choose nanoparticles that can be oriented in the polymer matrix? So to answer this question, we chose a block of polymers. So these are polymers that are formed by, in this case, by two blocks. One is called H and the other is T for head and tail, but they're basically equivalent and that these are completely symmetric. The advantage of using this block of polymer is that they can form very ordered mesophases, lamellar structure, or if you want, symmetric liquid crystal phases. You see some chains here, just to show you how they accommodate in these layers. Now, when we incorporate nanoparticles of different kind, we see that they can position themselves in some specific regions, domains of the polymer mesophase, or the lamellar phase. Neutral nanoparticles prefer to locate at the interface between the two blocks, the two polymer blocks. And the same thing happens when we have particles that strongly interact with one of either copolymer block, or when we have Janus nanodimers. They all position at the interface between the blocks. The only sort of nanoparticles that locate within the block are those that only interact very strongly with one of the two copolymer blocks, and they are within a given layer. So depending on what our interest is, we can tune this interaction different. We can design different nanoparticles to have them in precise location. Now, if we increase concentration, the tendencies are basically the same. They are still where we would like them to be. Up to 10% in weight, they are able to keep the same mesophase ordering. So the lamellar order is not disrupted. There can be some frustration in the way we see these lamellar phases, but the order is maintained. The system just becomes more crowded. What's the effect on the conformation of chains and the distribution of nanoparticles. These are the density profiles of chains. We distinguish the profiles of the orange line are referring to the H beads, to the H blocks. The light blue curves refer to the density profile of T blocks. And the solid lines is the sum of the two of them. So you see that the polymer is very homogeneously distributed throughout the system, with some decrease in density at the interface between the two blocks where the center of mass of chains are located. And what about the nanoparticles? So as I said in the previous snapshot, but this is of course more reliable in terms of statistics, the neutral nanoparticles are located at the interface between the blocks. The HH nanodimers are located within the orange, so the H block profile, and the Janus nanodimers located at the interface. So we can control their location. Now the question is, since these are anisotropic, it might make sense to align them. Can we control their orientation? So we calculated the polar angle distribution and the azimuthal angle distribution of all these sets of nanoparticles. The former is the angle between this axis, the nanodimer axis, and its projection on the lamellar plane. And the azimuthal angle is the angle between this projection and any reference axis we might want to define in the lamellar plane. You see that the azimuthal angle is basically flat, so the distribution is, all angles are equally probable. But if we look at the polar angle distribution, we see that the one of the neutral nanodimers is picked at 0 degrees. This means that the nanoparticles are lying flat at the interface between the lamellar planes. The HH nanodimers have a quite broad distribution. The difference line refers to different concentrations. That means that they are within the H block and there is not a preferential orientation. So they are randomly oriented. Now, if we look at the Janus nanodimers, H0 and especially HT, we see that the development of two peaks at approximately 70 to 80 degrees. What does that mean? It means that this vector here is almost perpendicular at the interface to the lamellar plane. So we are able to locate nanoparticle of a given sort into a precise position, and we can also orient them. And the orientation turns out to be quite high. So the alignment of these vectors of the nanodimer is quite high when we have Janus nanodimers of this sort with a nematic order parameter that is significantly large. So the conclusion is that they form a sort of nematic liquid crystal within a background ordering that has a symmetric signature, which is quite nice. So conclusions. We saw that size dispersity is actually a very interesting parameter affecting the mobility of nanoparticles in a polymer matrix. And it is a fundamental element to uncover the existence of universal behavior. We saw that at small scales in the dynamics of nanoparticles. We saw that in shear viscosity. When we increase the chain stiffness, we see an isotropic to nematic transition that affect the conformation of chains, that affect the mobility of nanoparticles and chains, but that also has an effect on the shear viscosity of the system. And finally, if we want to have a stronger control on where locating nanoparticles in a given polymer matrix, we then need to think what is the most suitable polymer architecture is and how we want to design nanoparticles. Because if two elements are properly selected, we are able to locate nanoparticles in specific domains and orient them according to what our preferences might be. So with that, I would like to thank very much the students who have made all this work. Javier Burgos, who is now at the University of Liverpool, and Oscar Alvarez, who is now at the University of Oviedo. Javier was my first PhD student a few years ago. Oscar was a master's student at University of Manchester. And of course, I'd like to thank the sponsors, and I would like also to thank you all for your attention. Thank you very much.
Thank you very much, Alessandro, for the very interesting talk. There is just time for a very quick question. So there is a question in the chat. Can you generate the initial configuration randomly instead than using Monte Carlo?
So we are using Monte Carlo actually because we want to generate a random configuration. And I think this is what we would like to have to avoid any possible correlation at any possible short or long distance between the species. So we can do that with molecular dynamics. Yes, we can. It just takes longer. Monte Carlo is very useful because you can make a lot of physical moves that speed up equilibration. So we just we thought that might be a good choice.
Thank you. So because we are just reached our time, I want to thank Alessandro again for a very interesting talk, and
thank you,
also
Paolo.
Professor Angeli as well. So we have now a short break of 15 minutes, so we get back at 11:30. I want to remind everybody that needs the certificate of attendance to contact directly Flora Stipperstein, either via the chat or emailing her, and then she will provide the certificate. So thank you very much, and see you in 15 minutes. Hello, everyone. So we start the second part of the first session, and we have two speakers. And the first one is Dr. Sébastien Grégoret from L'Oréal.
Hello.
Hello. Hi, Sébastien.
Hello, good morning.
Hopefully I didn't mispronounce your name.
Don't worry, don't worry.
Okay, so your talk is about in silico skin penetration modeling, a cosmetic Europe case study, results and updates. Very interesting. You can share your slide.
Yeah, let me know or I can do that because I am not familiar with Zoom.
All right, so there is a button at the bottom of the screen. There is a green button saying share screen. Can you try to click on it?
I saw actually, so I can send the arrêter le partage du participant. No, that's that one. That's not that one. So I saw actually the écran Philippe. And I choose that.
So, sorry, what did you say? So
ask for the control. I ask for the control.
Okay.
And then I share my screen.
Yes, try.
Okay, comment je fais ça? Sorry.
That's fine. So do you see the bottom? The at the bottom of the screen, the green see. Okay.
Okay, normally you should see my sorry, I really apologize.
So at the bottom of the screen there is there are various icons with the chart reactions. In the middle there is
I saw them. Affichage. Sorry.
That's fine.
Really. I don't know where is it.
You can't see the bottom.
No, I don't see anything else. I don't see anything else on the top.
No, the bottom, not the top.
On the bottom?
Yes.
There is participant.
Yes.
Share the screen.
Yeah, that one. That's what you have to click on.
Okay. Only one participant can share. Several participants can share. Only how I can share it. That's my concern.
All right. Wait a second, right? So let me see if I can.
Participant. I cannot.
You can't share this.
Click on the green screen, on the green arrow.
Yeah, I click on the green.
Arrow.
Okay, that's fine. I got it. Sorry. Normally you see my screen. It's fine?
We can't see your slides.
You cannot see my slide.
All right, I think something's starting. Just one sec. All right, there it is.
Sorry.
Perfect.
Sorry for the delay.
No problem. Okay, please.
So it's a kind of introduction. As you know, I'm not an expert of modeling. I'm much more a kind of experimental guy. So that's why I'm not always so efficient for such kind of things. So first of all, I would like to thank the Professor Siebertine who invited me to present these results that we obtained at Cosmetic Europe. So the talk is not focused on modeling on formula, but how we can use modeling in a different context. It's really the context of in silico skin penetration. So I don't know if you know, but for the cosmetic industry, animal testing is banned for any kind of reason. That means that when we have in mind to predict the risk associated to topical exposure, we have to consider two different things. So I use the example of the lion. We all agree that the lion is quite dangerous. I'm at home today, and I'm sure that even if a lion is dangerous, I have no risk to with the lion because I'm not able to meet a lion. However, if I want to go tomorrow to the circus or the zoo and to enter in the park where is located the lion, of course, I will increase dramatic exposure and I will take risk. It's the same thing for the cosmetics or any kind of chemicals, that the hazard is evaluated based on the properties of the chemical, and this hazard has to be combined with the exposure to perform the risk assessment. The exposure is also a product of two different components, the condition of use and the bioavailability. The HADME task force was created, I think it's 10 years ago, and led by Andreas Schepke from Bayersdorf and Nikki Witt from Cosmetic Europe to address this question. How we can refine the skin bioavailability to improve the risk assessment. The skin is the main route of exposure to cosmetic, and it's a very efficient barrier. That's the main function. One of the main functions of the skin is to prevent the absorption of chemicals. And of course, the idea is to perform the evaluation in as close as possible to the real condition of use. So I use the term of skin bioavailability, but what do we have in mind when we are talking about skin or cutaneous bioavailability? It's the sum of different components. The first one is the chemical is enter into the skin, and especially with the stratum corneum, which is the main limiting step for the skin. Then when it's entered into the skin and reach a variable part of the skin, it can be metabolized into different kind of chemicals. And then it's distributed in different skin layers and eliminated from the skin into the blood circulation, where other kind of aspects are effective in meaning metabolism by the liver, distribution in the body, and eliminated by the kidney. So and all of these components are is the sum. The sum of these components reflects the bioavailability. So, as you can see, this the bioavailability is a quite complex process, and the aim of the task force and the goal was to evaluate the different factors affecting the skin bioavailability related to local toxicity. When we say local toxicity, is mainly about tolerance and sensitization, or for systemic toxicity. For such purpose, we would like to provide suitable data for different components of the skin bioavailability using a large set of chemical with appropriate protocol. And ultimately, the idea was to use such kind of data to develop and optimize in silico model dedicated to skin absorption. For such purpose, the first thing was to select a set of chemicals, and we worked on a set of 50 chemicals that includes a large chemical space in terms of molecular weight and log P. We have some constraints. The constraints are based on the physico-chemical properties. So first of all, we would like to prevent very highly volatile chemical. We would like to have some chemicals which are enough soluble in water, and due to the different kind of protocols that we use, we would like to have radio labeling chemicals. So at the end, we defined a set of 50 chemicals, and we ran several different assays, set solubility of the different chemicals in different solvents. We measured also the ability of chemical to react with the proteins, knowing that this aspect is one of the key events for sensitization. We measured also the partition and diffusion coefficient of the chemical in different skin layers. Skin metabolism was also evaluated through two different approaches with skin ex vivo human skin, and also on subcellular fraction. And at the end, we measured the skin distribution of the 50 chemicals in a standardized protocol. All of these results were published with the list of the reference reported here. Here is the classical skin distribution protocol. So I don't know if you're familiar with such kind of protocol, but let me explain how we do that. For such kind of study, we are using human skin abdominal human skin coming from plastic surgery. The skin is set up on France cells that define an exposure area, and it's made of different kind of components. You have the skin, you have a cap which defines the exposure area, and the receptor compartment is filled with the receptor fluid mimicking the blood circulation. The skin is well controlled and so on in terms of characterization, in terms of integrity, temperature, and so on. Then we applied a given volume of the solution, 10 microliters per centimeter square. Then after 24 hours, the skin is washed to remove all of the chemical remaining of the skin surface. Then the different skin layers is separated. For the stratum corneum, it's obtained by tape stripping, meaning successive different tapes. The epidermis and dermis separated by heating, and then all of these samples are extracted, and the amount of chemical was determined by scintillating counting. Here is it, and so this protocol is compliant with the OECD guidelines. Here are the typical results that we obtain. So I reported one of the results for cinnamaldehyde, for example, and we determined the fraction of the chemical found in the different skin compartment, meaning it was the chemical remaining at the skin surface, stratum, epidermis, dermis, and receptor fluid. And we also provide the kinetic of the penetration of the chemical through the skin. So that's all of the set of the data that we have. Then the idea was to use, okay, what is the performance of the actual in silico model to predict the skin penetration? We work on a subset of 25 chemicals. We evaluate 6 different models listed here. For all of the evaluation was done by some person having some enough experience with each model, and to all of the people we provide the same set of data, including chemical name, physical chemical properties, partition and diffusion coefficient measured in the stratum corneum, and the condition of the exposure, meaning vehicle, pH, skin thickness, and the mass balance. The mass balance is the sum of the amount of chemical found in the different compartment normalized to the amount applied initially. So I just precise the condition of the exposure. It was finite dose of vehicle, meaning 10 microliters per centimeter square, which is a small droplet. 24 chemicals were solubilized in water, and 4 chemicals were solubilized in ethanol. So over the 6 models, one was discarded because the model was able to predict only the permeability coefficient. And we were interested by the amount of chemicals that is able to enter the skin and to reach the vital part of the skin, meaning the epidermis, dermis, and receptor fluid. So all of the rest of the evaluation was done only on 5 different models. The first thing is the effect of the evaporation. Here, the graph reports the mass balance. I just remind that the mass balance is the sum of the amount of chemical found in the different skin layers normalized to the theoretical amount, to the applied amount. And if everything is fine, normally the mass balance should be at 100%. You should not lose chemical whatever. Here, in that case, when we plot the mass balance as a function of the vapor pressure, we can see that after a given value for the vapor pressure around 0.01 millimeter de mercury. Sorry, I don't know the words for mercury in English. So we can see that for such kind of chemical having high volatility, the mass balance decreased. That is related to the volatility of the chemical. Of course, a part of the chemical can be lost, simply because it's evaporates over the time. So the idea was to know at the first intention if the model are able or not to predict the chemical volatility. Over the 5 different models, 3 models were able to predict the chemical evaporation, and here it's reported the predicted evaporation as a function of the estimated evaporation. And the estimated evaporation was the difference between the mass balance at 100%. As you can see, more or less the model are able to discriminate between non-volatile chemicals, which are reported here compared to the very highly volatile chemicals, but the correlation was not so good. Then the other things. I just remind that when I said at the beginning that the skin, the main component of the skin that's limiting the skin absorption is the stratum corneum coefficient. Sorry. It's the stratum corneum. And the stratum corneum is characterized by 2 different parameters, which are the partition coefficient and diffusion coefficient. We have 2 ways. It can be predicted with some models, and all models involved have some model to predict the partition and diffusion coefficient, or it was also measured, and that's one of the papers that we published. Here, for one model, we saw the impact of the difference between predicted and measured partition and diffusion coefficient. It was a Simlumation model, and we can see that for this model, we improved the overall correlation. Nevertheless, it cannot be seen as the general rules, because here are the reported the coefficient correlation for the different models, and depending on the models, sometimes it don't change, it doesn't improve the correlation for the Surrey model, and for some others that it could be better to use predicted rather than measured coefficient. The reason for that is that the protocol used to measure this partition and diffusion coefficient was done, I reported the experimental condition, it was done in infinite dose, meaning a large volume of vehicle. That could explain why it's not the measured partition and diffusion coefficient cannot always improve the performance of the model. That's one of the key points, is that meaning that we have to use a protocol which is compliant with the experimental condition. Here is reported the list of the different, the results of the different models to predict the dermal delivery.
Sebastian, could you please talk in front of the microphone, because I think when you move your head, then your voice disappears. All right.
Sorry. So I said so here's the results that we obtained for the 5 different models, and we predict the dermal delivery, meaning the amount in the variable part of the skin. The gray correspond to volatile chemicals, the black correspond to non-volatile chemicals. And as you can see, some of the model were more or less performant, and one of the most appropriate model was the model TCAT from Simulation Plus. I just precise that this evaluation was on date, and of course, if we perform again this simulation with the new version of each model, I cannot guarantee that the result is the same. Here, because I just remind that also that we are also interested by the how the chemical is distributed into the skin, and that could be of interest, especially for the local tolerance, as the local toxicity, sorry, as a local tolerance or skin sensitization. As you can see, if more or less the model, some models are the ratio between predicted and measured value are more or less close to 1. As you can see in the different skin layers, it can be really, really worse. The TCAT model, which provides the best correlation for the dermal delivery, shown the amount in dermis is largely overestimate, whereas the amount in stratum corneum is largely underestimate, and the amount in epidermis is, well, the mean is around 1, but it's the individual value are spread quite largely over this mean value. So none of the models are able to predict accurately with good precision the amount in the different skin layers. So I heard the previous presentation. Of course, it's not emulsion, so it's a kind of simple aqueous solution. So anyway, we evaluated in our study not a complex formula, but we also compare simply water and ethanol. We know that normally ethanol acts as a chemical enhancer and should promote the absorption of the chemical in and through the skin. But as you can see here, in black corresponding to the experimental value for the aqueous solution, and here in dotted bar correspond to the value with ethanol. For the three tested chemicals, with ethanol, the skin absorption decreased. It is really related to the fact that we are applying at finite dose, finite amount of vehicle was applied, and the ethanol should evaporate before entering into the skin and affecting the barrier function of the skin. All of the models shown great difference between all of the models predict lower dermal delivery with ethanol, but with some huge differences. For example, for the CDC model, for the geraniol, it predicts lower dermal delivery, but with a lower impact compared to the experimental value. Whereas for the parabens, the model predicts much more lower absorption with ethanol compared to the experimental value. So that just means that for simple vehicles such as ethanol, the models are not so well, any models are not so well effective to predict clearly the behavior of the formula. I just remind the conclusion of this first evaluation. First of all, the skin metabolism was not taken into account in this study. The chemical volatility should be considered in the model, and now it's integrated in the TCAT model. The dermal delivery, meaning the amount in the variable part of the skin, is more or less well predicted only for a PBS solution. And the other thing is that we have a subset of 25 other chemicals, and when we evaluate these additional 25 chemicals with the TCAT model, the performance was worse. And one of the reasons that this second set of chemicals include also reactive chemicals. And I said at the end that there is lack of performance to predict the effect of the solvent. So that's why the first part of the study. Of course, cosmetic formula are not simple aqueous solution, are not simple ethanolic solution. So we want to evaluate the performance of the model with much more cosmetic kind of vehicle. And we, for such purpose, we evaluate caffeine in two different emulsions. We evaluate water in oil, inverse emulsion, and a direct emulsion. Caffeine was solubilized in this formula at 0.5%. And we perform on these experiments, on these two different formula, a different set of experiments. And I will present some of them partially. For the formula characterization, we characterize the evaporation rate. And as you can see, depending on the type of formula, the inverse and the direct, the shape of the evaporation rate is different. And it reached ultimately a limit corresponding to the amount of water in the formula, which is the main component reflecting the volatility. We determine also the concentration in the saturation of the chemical in the aqueous. As for the other study, we performed the classical skin distribution. I don't want to insist so much on the results that I've already shown. Just one thing, there is no significant difference except for the stratum column between the two formula. We evaluate this classical ticket model as I reported here. I just want to insist on these parameters that we need to have partition and diffusion coefficient for stratum corneum, but also for the different skin layers. And we have 3 ways to have access to this partition and diffusion coefficient: calculated, measured through the skin distribution data that we obtain, or measured on isolated skin layers. The last point is about the dosage form. We evaluate 2 different options for the dosage form: emulsion or solvent. Here are the results for the caffeine in the inverse emulsion. And we also here compared different ways to implement the partition and diffusion coefficient. It's the skin distribution, the percentage in different skin layers, the percentage in dermal in the receptor field, and the kinetic in the receptor field. The blue correspond to the incremental value, and the 3 other bar graph correspond to the 3 different options for the partition coefficient. The first one corresponds to the calculated one, and is not really, it doesn't provide really relevant information. I just remind that the caffeine for the evaluation with the aqueous solution, the predicted TCAT value, the predicted partition diffusion coefficient was really appropriate. When we measured the partition and diffusion coefficient, it is really not so effective. And we used the partition diffusion coefficient measure on isolated skin layers, which provide the best adequation with the experimental value. So for this type of formula, the measurement on isolated skin layers is much more appropriate, knowing that we still underestimate the amount in dermis. But it's not a general rules, because when we perform the same thing with the direct emulsion, none of the of this approach was appropriate. But another thing was that we have to consider it's the type of dosage form. So here in this plot, it corresponds to here you still have in blue the experimental value, or here in red the experimental value. This bar graph corresponds to the formulation when it's modelized as a cream, and this in dot correspond when the formulation is modelized as a solution. As you can see, for the inverse emulsion, the most appropriate is to simulate the formula as a cream, whereas for the direct emulsion, the most appropriate is to simulate the formula as a solution. That could make sense if you consider that the continuous phase of the direct emulsion is the water. So we can assume that for direct emulsion, maybe the most appropriate way is to characterize as a solution. So we can use TCAT model to simulate skin absorption. One of the things is that for the formula, we have to consider 2 parts in terms of optimization. First of all, we need to optimize we need to select the most appropriate dosage form. And the second thing, we need to select the most appropriate partition and diffusion coefficient. We assume that the formula affects the partition and diffusion coefficient of the stratum corneum, as it's directly in contact with the formula. And the partition and diffusion coefficient of the deeper skin layers, meaning epidermis and dermis, should be less affected by the formula. And the idea is to measure this partition and diffusion coefficient for epidermis and dermis in a different experiment, which is independent of the formula. Clearly, the future challenges are to define the formulation characteristic driving the skin absorption. So that's in such a way we expect that we are much more able to add the appropriate characteristic of the formula in the model. The second point is to design and validate standard protocol to measure this partition diffusion coefficient and to define the way to use this value with different PBPK models. The other main difficulty is that all models do not use the same kind of parameters. Have in mind that for the TCAT models, the partition and diffusion partition coefficient are normalized to water, whereas for other PBPK model, the partition coefficient are defined between continuous skin layers, meaning for the partition coefficient between epidermis and dermis is defined at the partition coefficient between epidermis and dermis for Simsip, but for TCAT, it's partition coefficient between water and epidermis, or partition coefficient between dermis and water. So that's all of the things that I can say on this topic. I realize that it's a little bit far away from the other presentation done today. I would like to thank many people involved in this study. I'm quite sure that the list is not complete. And all of this work was done with the support and with the expertise of the guys involved in this. And thank you for your attention.
Thank you very much, Sebastian. Unfortunately, there has been some problem with the audio, but I think most of the people got basically everything. So there are a few questions which I think partially has been answered by people in the chat, but maybe I can just quickly ask. So we lost your audio when you were talking about the derm-win model.
Yeah.
And why was it discarded, that one?
So it was epiderm-win. So the epiderm-win predict what we mean by permeability coefficient. And the permeability coefficient is a kind of properties which is only focused on the amount in the what we name its receptor fluid, meaning the amount in the blood circulation. Moreover, such kind of parameters is compliant when the experimental is done with infinite dose, meaning a large volume of vehicle applied on the skin. That's why the outcome of this model was not compliant with the experimental protocol we used. And also it was discarded for that reason.
Okay, thank you. And then there was a question from Jo Cook from Unilever, but she said that it was answered during your talk. Okay, so if there are no other questions, thank you again very much, Sebastian. And then we can move on to the last speaker of today, Sander van Loon from Van Loon Chemical Innovation. Hello. Hi, Sander.
Yes, hello.
Hi.
Good afternoon.
Good afternoon. So, Sander, we talk about the digitalization of formulation R&D via science-based web apps.
Yes. Thank you very much. And thank you all for giving me the opportunity indeed to tell something more about the digitalization of formulation R&D via science-based web apps. You can all see my screen properly?
Yes, we can. Thank you.
Okay, cool. Right. Indeed. So my name is Sander van Loon. I'm the founder of Van Loon Chemical Innovations, VLCI. And we are a small group of formulation enthusiasts and striving to accelerate your chemistry. We do that by the practical implementation of predictive formulation sciences, HSP and HLD, which I will explain further in this presentation. And we combine that with high throughput screening. I will also tell you why we need high throughput screening in order to make science-based formulation happen in the industry. So we work for companies all over the world in the field of personal home care, coatings, polymers, agrochemicals, well, everything that has to deal with formulation developments. And nowadays, we are also selling licenses on our web apps, which will be further explained in these presentations, including some practical examples. I see already a lot of presentations with a lot of modeling and a lot of equations and data. I think this presentation is a bit more practical than that, and I hope you will like it. So, why are we so much focusing on HSP and HLD as a formulation science to implement the formulation developments? Well, that is because HSP is applicable to solutions and dispersions, so not only to solubility, as the name suggests. So we are changing the name actually to Hansen similarity parameters, and I will explain you a little bit more about that. It's a very effective matchmaking systems in order to give a practical parameter to ingredients in order to formulate solutions dispersions, but also to some extent, when it comes to compatibility between surfactants and oils, you can also apply it to emulsions. But if you really want to develop specific emulsions, like water in oil, etc., then the HLD, the hydrophilic lipophilic difference, does not the balance, but the difference makes a lot of difference, is there to give practical parameters to surfactants and oils, and based upon the equations, you can then formulate your specific emulsions. And both those sciences we also apply as a service in our company in order to determine them for ingredient suppliers, for example, but also to implement them for formulators. So using those two formulation sciences, you can actually develop any type of product, a solution, a dispersion, and an emulsion. So it doesn't matter what kind of product, like a personal care, home care, coatings, etc. Every type of product can be developed via those sciences. And because they work from the inside out, from the ingredient parameter, you can match ingredients together. And because of the thermodynamic equations, they like each other when they are matched. So it's a matchmaking system, actually. We also make it online. It's almost like a dating app. But when doing so, everything performs to the utmost. That means you can improve your properties. And I already saw now the presentation about efficacy, for example. You can also improve the efficacy of your formulation by using HSP, for example. So there will be an example later on in this also. We're also talking about rheology in the beginning of this Congress. This can also be tuned by applying HSP or HLD. So there are a lot of opportunities to improve your end properties of formulations by applying those sciences. So Hansen similarity parameters, how does that work? It is a sustainable, predictive ingredient parameter in order to develop solutions, dispersions, and to complement emulsions, as I mentioned. It consists of three parameters: the delta D for dispersion, the delta P for polarity, and the delta H for hydrogen bonding. So three parameters. And you can obtain those parameters for all kinds of ingredients out there used in formulations. So polymers, oils, solvents, pigments. Yes, there's also things that doesn't dissolve. There are two ways in order to get to an HSP. You can calculate it based upon the smiles of an ingredient, but it's rather difficult for polymers or complex structures. So the correlation between the practical use is a little bit less than when you do the experimental HSP determination. And that is how we normally determine HSP. So we have a set of solvents of which we know the HSP of. We add an unknown ingredient to it. We go to rate all those solvent samples. We enter it in the software from Hansen, the HSP IP, and then we generate the center coordinate plus the sphere. So if you calculate values, you only get the center point. But if you do it experimentally, you will get the center plus the sphere. And the sphere says something about the range of compatibility of your ingredient, actually. So that is your like region. And if other ingredients are inside that bubble, that sphere, then they like each other. That means they form something stable. The beauty of HSP is that it can be sustainably used because it is a fixed parameter. So every ingredient has its unique center coordinate and radius. So matching ingredients is now possible because if another center of an ingredient is inside the sphere of another, then they like each other. So therefore, you can develop complex formulations with HSP by mapping all those spheres into Hansen space. So there are equations for it to measure the distance, the center-to-center distance, and if they are inside the radius. So that means that the center-to-center distance is divided over the radius. So if the RAD is below 1, it is inside the sphere. So the blue dots in this picture. And if it's above 1, it is a red dot. That means it's less compatible. If it's too far away, it is not compatible at all. So here are the ones that are very good inside the sphere, and then less and less and less, or even non-compatible ingredients. Sometimes you also want to know to which ingredients your packaging material, for example, is non-compatible. So to make sure that that doesn't leak through your packaging material. So this is how you can formulate with HSP, by using those equations, the distance equations, in order to find other ingredients for your formulation. Then HLD, hydrophilic lipophilic difference, only applicable for emulsions, to develop specific emulsions. Again, it is a predictive ingredient parameter, in this case for oils and surfactants, and also can be used in a sustainable manner. So this is the equation. The HLD equation takes into account the salinity, either the external salt that you add, or that comes from a ionic surfactant, for example. Then the EACN, the effective equivalent alkane carbon number. That means how oily your material is. It's applicable to oils, mineral oils, vegetable oils, but also for monomers and polymers, etc., etc. The higher the number, the more hydrophobic a material is. You can also blend ingredients together and calculate the blend EACN. Then the temperature, the deviation from 25 degrees, and the CC is the characteristic curvature of a surfactant, applicable to all kinds of surfactants: synthetic, bio-based, ionic, non-ionic, etc., etc. And again, you can make blends of ingredients in order to get to a certain CC. The higher the number, the more hydrophobic a surfactant is, the more it likes to be in the oil. Then you have FA, which is used for all the other additives like fragrance or preservatives, etc. They also have an influence on the balance of your emulsion. So then the HLD is your equation or your guidance in order to develop specific emulsions. HLD 0 is the microemulsion region. That's where everything is happy together. Like the HSP, where everything is thermodynamic stable. That means it doesn't really form an emulsion, but it's more like a dancing solution, let's say, where you can find the lowest viscosity, for example, but the highest stability of your formulation. You know? So that is normally how we determine EACN or CC values of unknown ingredients, because when we fill in 0 in the equation, we know, and we have a scan of which we know all the ingredients, and then we add one unknown to it, one unknown oil or one unknown surfactant. And based upon the blending rules, we can calculate back what the CC or the EACN of the unknown ingredient is. Once you have it, then So if you have your ESCN blend, your salinity, temperature, you can then calculate which CC do you need in order to get to a certain HLD 0 point in order to select your surfactants. Again, you can make a mixture of surfactants in order to get to the required CC. I will give you some examples. HLD below 0 gives you the oil and water emulsion. And the best region for this oil and water, the classic emulsion, let's say, is around -1, where you have the smallest droplet size and the best stability. On the other end, HLD above 0 gives you the water in oil. Again, around +1, you will get the smallest droplet size and the best stability of your emulsion. Yeah. So whatever you fill in it for HLD, you can always calculate which CC do you need in order to develop that specific emulsion. So, and again, you can then find your best surfactants, blend them together in order to make the emulsion of your ESCN oil, a monomer, polymer, whatever you want to emulsify. So with both, you can predict compatibility and improve performance and better understand the interactions between ingredients. You can reduce complexity because you can streamline the number of ingredients, so using less materials, ingredients in your formulation and their concentration. You can also do replacement of ingredients. Once you know the area of HSP or HLD, you can find alternatives with same parameters. Yeah, so then you can easily switch to bio-based solvents, for example, or bio-based surfactants, etc. You can also make specific ingredients compatible. If you have ingredients that doesn't overlap or doesn't match, you can find something in the middle in order to bridge those ingredients to make them compatible in your system. You can tune blends. For HSP, you can tune blends of solvents in order to get to a certain HSP value. And for HLD, we can then tune blends of ESCN or CCs in order to get to a required parameter. But most of all, it is sustainable data. Once you have the HSP and HLD of your ingredients, it's fixed. And that's why we are using this in order to digitalize R&D. And that is how we differentiate from all the other digitalization approaches, where you always need experimental input in order to build your models. And here it doesn't. You use HSP and HLD in order to select your ingredients, etc. But there's a small problem because science-based formulation is quite hard and people find it difficult to understand. And there are so many ingredients out there and not so many HSP and HLD of commercial ingredients. It is very time-consuming and it's an error-sensitive task. So if you have 10,000 of ingredients out there, it will take years. So people always see the big mountain like, oh my God, I'm not going to do that because, yeah, you know, we have to make a lot of samples, we have to characterize them and blah, blah, blah. So the solution is simplify it and make it accessible. And we do that via automation and web apps. So preparing those samples in order to determine HSPs and HLD, as I said, with a set of scans that we know the parameters of in order to get the unknown. We do that already via our Formax, that is a high throughput system from ChemSpeed, where we can prepare all those samples and also the formulations. But we still have to characterize all those samples because we make hundreds of samples. So while we make, let's say, 50 samples per ingredient in order to get an HSP or an HLD point. So you can imagine how many samples that we need. We developed formulation apps using a central database. And I will explain you more about that. But in order to get the sample evaluation done right and more accurate, we are building robots in order to screen those samples that we prepare. So then we can finally screen a lot of samples and get their HSP and HLD, because we're using picture analysis in order to screen all those samples that we prepared and say, okay, this is an emulsion, blah, blah, blah. Here's your HLD 0 points, so we can determine the ESCN or CC values. Or these and these solvents are good solvents, so that means here is your HSP point of the unknown. So that is how we catalyze actually the implementation of science-based formulations, HSP and HLD. So we have created the world's largest central HSP and HLD database. We call that PredictID, Predictive Ingredient Database, where we include our own, of course, non-confidential data from commercial ingredients. And we also working together, as you can see here, with suppliers in order to get their ingredients in this database as well. And they can even link that to their own digital tools. If they don't have it, they will get a bunch of HSP or HLD for free, because we want to build this database further. And most of all, our users can guide us on which ingredients they want in the database. And that is actually good, because now more and more ingredient suppliers are aware of the use of HSP and HLD, that our formulators are in a need in order to have those values available in a database so that they can start formulating. So with this database, we connect that to our web apps. We call the HSP web app PrettyMatch. It's here on the left side. And PrettyMilsion is our HLD-based web app here on the right side. So with those apps, you can see that all those ingredients are now data points in the app. And you can narrow down formulation space a 10-fold in order to develop your coatings, inks, personal and home care products. Yeah. So people are using the central database, of course, in private, but everyone can use this data in order to develop their products, to select and visualize their ingredients, find matching ingredients, compatibilizing ingredients, and replace ingredients via the central database. But you can also privately load your own database. Nobody else will see that. And of course, with both, you can privately formulate your ingredients, your formulation. And each ingredient will perform to the utmost. Some PrettyMatch examples. In the database, you can filter through the ingredients that you're looking for, the type of ingredients or suppliers or whatsoever. You can then bring them to your formulation. So these are the ones that you want in your formulation. This is your lab bench, let's say. Or to select ingredients, and those are the ones to select from. And the app gives you all the calculations in order to find the best ingredient for your system. How does that work? For example, if you want to solubilize a solute, in this case, an active ingredient, Pantothena beta from Res Pharma, in order to solubilize that in a certain emollient solvent blend system. You load it to the formulation ingredients, all your emollients in select ingredients, and the app calculates what is the RAD. So if it's in or outside the sphere of your ingredient. And as mentioned, it should be below 1 inside the sphere, and the closest, the better. In this case, you can then select the best performing emollient and then solubilize your ingredient. And as you can see in this table, the further away from the center HSP of my active, the less you can solubilize. So it's very good to be targeting the right center HSP of your ingredient in order to have the highest solubilization. Yeah. You can also make ingredients blends for solvents, for emollients in this case, even though they are non-solvents by themselves. So you can make a blend which is inside the sphere. So once you have that, you can find other matching ingredients like surfactants, additives, etc., etc. So solubilization and then formulating is a little bit different than dispersing. Dispersing should not be too close to the center, your polymer, in order to stabilize your particle, because else it will agglomerate. But also not outside the sphere, of course, but around RAD half. So that means halfway, facing your solvent system. In this case, we want to disperse a pigment, a carbon black, Printex G by Orion, with a waterborne dispersant. Again, we can map all those dispersants in Hansen space. Based upon RAD, you select then the best dispersant. And also here we have seen that indeed around half RAD, you will have the lowest concentration of dispersant needed in order to stabilize your pigment in your water-based coating. Once you have it, again, you can select other ingredients, make blends of coalescents, for example, for your binder system, etc., etc. So here's a picture of when adding your pigment, dispersant, and underneath you have your binder plus your coalescent. Yeah. So once you have that, you can then prepare your paint into your lab. So HSP, solubilization, dispersion. Pre-emulsion is HLD is more about emulsions. Yeah. Applicable to also to polymers, or in this case also to monomers. As mentioned, the ESCN is required in order to start getting an insight in the HLD equation. So in this case, we selected butyl acrylate and vinyl acetate in a ratio 30-70, and the blend ESCN is then -1.7. We enter that into the app where we can calculate, okay, HLD should be below 0, something minus, not too far away from HLD 0 in order to develop my oil and water emulsion. So you can just put the sliders to where you want, and then it calculates, you need a CC of -0.2, sorry. And it can also suggest which surfactant do you need in order to emulsify that specific blend. In this case, lauryl glucoside is used in order to make this emulsion happening. We are still further developing pre-emulsion. So while Predimatch is already launched in the market, pre-emulsion is still in the development phase. Even though, so this was an example about an ESCN blend. This example is more about to develop a CC blend in order to match to the required CC that you need. Here we are going to develop a microemulsion of squalane for a personal care product. The ESCN of squalane is 22. Filling that into the equation at room temperature, it then calculates that you need a CC of 3.7. We had the choice about bio-based surfactants, SPAN 80 and polysugarmules D6. Here are their CC numbers. So you can calculate which ratio of those two you need in order to get to the required 3.7 CC that you need to microemulsify the squalane. Once you predict that, then you go into the lab in this range in order to define the best range of surfactants, ratio between surfactants in order to make the microemulsion, in this case for squalane. Yeah. And it falls into the range of the predicted values, actually. So once you have this, then again, you can add all your other ingredients to it and adjust the ratios. Right, to conclude, with those web apps, we provide sustainable and collaborative formulation R&D. Yeah. That means you can narrow down a tenfold your formulation space for the development of coatings, inks, personal and home care products. You can find 100 times faster your matching, replacing and compatibilizing ingredients via the sustainable use of those predictive ingredient parameters, HSP and HLD, and in order to increase the performance of each single ingredient in your formulation. to have the best performance and the lowest dosage of your ingredients. So everyone can join this science-based formulation movement. You call it more a movement, actually, because now we see in the market that a lot of companies are pushing in order to get science-based formulation implemented, because it will save you so much work. And you get a better understanding of your formulation design than you could ever had with, trying and see what's happening. The beauty of a licensee is that we continuously upgrade the database. We have a lot of collaborations with ingredient suppliers. And we're adding more ingredients. Formulators are pushing for more ingredients, and users, they can guide us on the ingredients they want in this database. So collaboratively, we add all those ingredients, and sustainably, we are using them in private in order to develop your formulations. Once you have developed them, then you can experimentally validate them in the lab. So that will drastically save on time, samples, and costs. All right, so this was my presentation. Thank you very much. And yeah, together we can make it happen.
Thank you very much, Sander. So thank you very much for a very interesting talk. There are a few questions. It would be nice if we can answer those very quickly, perhaps. So the first one is from the previous speaker, actually, Sébastien Guegaud, asked, what is the sensibility of the HSP and HLD measurements to the quality of the raw material?
Yeah, indeed. So we determine of the products as is, indeed. So it has a direct practical link to your lab work. So indeed, it can be, ingredients with impurities in there, et cetera, et cetera. So we don't do the calculation values because they are very precise in a pure ingredient. With the experimental determinations, we use the product as is. So we take into account all the impurities or the solvent system that it is delivered in. So with that, it has a very good link to your lab work. But yes, they are sensitive indeed to impurities, yes.
Thank you. So the other question is from Phil Jill from Raxol. And so the HSP, does the sphere size change significantly with the molecular weight and polydispersity of a polymer? This is actually related to a work I've done myself as well, where we've been trying to see if we could predict the solubility of a polymer as knowing the solubility of a monomer, because this should depend, right, on not only the molecular weight, but also the conformation, if it's in a good solvent or in a semi-good solvent.
Correct. Yes. So besides that, every ingredient has this unique center coordinate. It also has this unique sphere. And the sphere indeed can differ from a highly cross-linked polymer using the same monomers, for example. So if you have a very highly cross-linked polymer, high molecular weight, then the sphere is very narrow, a very small radius. But if the molecular weight is less, then the sphere is bigger. So that means it solubilizes better into a wider variety of solvents indeed. So that's where the difference is. And again, if you do the experimental HSP, you will get insight about the sphere as well.
But do you have any way to predict the size of the sphere depending on the molecular weight, or even if you have branched polymers, for example?
No, unfortunately not yet, no.
Okay, perhaps I can share my paper with you so you can have a look if you find it useful.
Cool. Yes.
It was on a very, very simple polymer, so perhaps not very applicable. So there are a few others.
Yeah. Mm-hmm.
So there are a few other questions. One is about, could this be applied to foodstuffs too? Do you have food safe ingredients in your database?
Not in my database, indeed. We also work for the food industry, but not so much actually. But yes, also there they're using ingredients indeed from which we can determine the HSP value. We did that also. So it's also applicable there. Yeah, also for surfactants, for example, or natural surfactants, as they call that, stuff like that. Yes, definitely applicable, both HSP and HLD, by the way. Yeah.
Then I'll try to go through as many as possible. So is it possible that
questions. Okay.
yeah, a lot of people ask a lot of questions. So is it possible that we might be able to predict HSP parameters from molecular formulas if only the lower molecular weight materials, even if only for low molecular weight materials to begin with?
Yeah, as I mentioned, so there's a database of HSP values for building blocks as well, for polymers, indeed. So you can already calculate that. Yes, that's possible. It's not in our app, but it's in the software from Hansen himself. Yeah.
Yeah. And then I think that was related to the machine learning one, using the SMILE, the SMILE, of course. Then the last question is, you mentioned the solubility parameters can be calculated, but most often are obtained experimentally. Is that correct? Do you still expect amount of work to characterize them to be a problem?
No, well, that's what I addressed here in in this presentation. People see that it is a lot of work in order to do the experimental HSP or HLD determinations. But with our workflow on high throughput and building those robots for evaluating the samples, we can really speed up the characterization. So there's the HSP and HLD determinations. So that lowers actually the hurdle for people in order to get started with HSP. And then in our database, we have more and more, every month, this pile of data is growing. Yeah. So, yeah, and we can easily scale up robots. So we are ready for it. Yeah.
Okay, I think I went through all the questions. Thank you very much again for your very nice talk. Thank you to all the speakers of this session, very interesting sessions with a lot of different topics covered. I want to remind everybody that needs a certificate of attendance to please message directly Flor Sipperstein from the chat rather than me, and also not send emails, please. I was mistaken in my previous message. So please just message directly Flor Sipperstein to receive a certificate of attendance. So with this, I want to thank everybody again. And we have now 1 hour lunch break. And then we are back at 1:30 with the second session. Thank you very much, everybody. See you soon.
Hello, everyone. Welcome back after lunch. I'm chairing the first afternoon session. I'm Charlie Wan from the University of Exeter. And before we start with our first speaker, I just have two quick updates to let you know about. So the first one is a certificate of attendance. If you need one, please send Floor a message in the Zoom chat, but please remember to include your full name and affiliation and the email to send it to so that we can make sure it gets to you all right. And the second bit of admin is Phil has put feedback form in the chat, and it would be really great if you could go and fill that in and give us some feedback. There's also a link on the slide in front of you with it. So moving on to our first speaker of the afternoon of what promises to be a good session. Our first speaker is Dr. Mehdi D. Dalvari from the Leibniz Institute of Plant Biochemistry over in Germany. And he's going to be talking about developing sustainable detergents through integration of computational modeling and protein engineering. So I'll pass it over to you.
Do you hear me well?
Yes, we can hear you.
Okay, and do you see my slide?
Yeah, we see your slide. If you want to put it
Great.
Presentation mode. There we go. Perfect.
So, hello, good afternoon, everyone. I hope that all you hear me well. So first, I would like to thank the organizer for providing the opportunity to present in this wonderful conference. It's really nice to be here. And today I would like to specifically talk about our experience on how we can use computational modeling with combination with experimental techniques to design a sustainable detergent. So I would start with a brief introduction about enzyme and the role in detergent. As you see in this figure, enzymes are used in many different industrial sectors. But there is also increased demand and interest to use enzyme in different applications. And one of the largest application, which holds about 30% of the enzyme market, it's enzyme used in household and laundry. So it's expected the market for enzyme in total to reach up to $20 billion by 2025. And 1/3 of those enzymes are used mainly in household and laundry. But why we use enzyme in laundry? In principle, modern detergent, as you see here in this figure, are composed of several ingredients, including mainly surfactant, which are used to stabilize soil, softener or builder, which are mainly based on the polymers. And enzyme, as you see, there are different classes of enzyme are used in detergent and other ingredient. Here you see that enzymes are an important part of the detergent, and several enzyme classes are used to remove different substrate. And one of the most important enzymes in most of the detergent are proteases, as you see here. So proteases are used commonly to remove protein-based stain like egg, blood, or grass from the fabric stains. And there is a high demand to use enzyme in detergent due to the sustainability, and there is also always unbroken need to identify new enzymes which are highly performing and can be used in detergent. But as we know, enzymes are biological catalysts, and they have some challenges when they are used in environments such as detergents. So they have to tolerate high temperature, very, let's say, alkaline pH, which are used in the detergent, and they have to also tolerate a lot of harsh chemical, including surfactant or oxidating agents. So this means that there is also a big bottleneck in development of novel detergent based on biological catalysts to develop always enzyme which can tolerate such a environment. And as you see here, there is also high trend also to use enzyme because we could use detergent at lower temperature to have higher performance. But how we can design enzyme? In principle, as for non-biologists, so enzyme can be engineered using enzyme engineering techniques. in principle, they are classified into 3 categories. As you see, methods rely on directed evolution, rational design, or semi-rational design. So in directed evolution experiment, which are in principle based on natural selection. So the idea is that you have a protein, so which is encoded by amino acid sequences. You can generate a random mutational library, and then you can use a selection criteria or a high throughput screening system to identify better variant using a functional assay and then characterize them. So this relies mainly on experimental techniques, but there will be no general molecular understanding from the improvement of enzyme. So due to the importance of this method, Frances Arnold, one of the Nobel laureates in 2018, was awarded the Nobel Prize. But now, based on existence of more protein structures, so we have method rely on computational design. As you see, in such a method, we use the knowledge from a structure-function relationship of protein to identify a specific position in an amino acid chain of a protein, and then to use method of mutagenesis to identify better variants. So mainly here, so we know that there are 20 amino acids in the nature, so we could exchange one amino acid with one other amino acid to identify better enzyme in the new environment. So these are mainly rely on so-called site-directed mutagenesis. But as you see, compared to the direct evolution approaches here, we do not use the diversity offered by nature. That's why semi-rational methods are defined, which are in principle a combination of both methods. So here we identify a position using computational techniques, but we try to generate a mutation library in a specific position. And during my talk later on, you will hear this word. So we use mainly so-called a site-saturated mutagenesis. This means that we could exchange one amino acid in a protein with 20 other amino acids. So there is a big trend to use such a method because we could reduce much experimental effort and to accelerate the protein engineering campaigns. So with this background, I would like to focus on the topic of today. So the project that I am presenting today was performed in so-called HiCast. HiCast stands for Henkel Innovation Campus for Advanced and Sustainable Technologies. And this project was funded by Henkel, one of the key players in enzyme, in detergent. And as you see here, the idea and the aim of HiCast was to understand, to develop more sustainable and novel detergent using molecular understanding of interaction between the enzymes, surfactant polymer in the formulation, and the material surface. So for this 4 different expertise of 4 different groups at University of Aachen, my former institution, we team up in order to understand the interactions and also to design the formulation. So as you see here, so we used method based on biotechnology or protein engineering, catalysis and synthesis, method rely on colloid, and computational modeling. So today, I would like to present one of the highlights of our work. So our first investigation in HiCast shows that in one novel detergent, we could, by combination of some polyelectrolyte, as you see here, we could have much better performance of and cleaning of a surface. So you see clearly by combination of enzyme and polymer, you have much better cleaning on the surface of the cotton. So we call this effect a boosting effect. And due to presence of the enzyme, we believe that this has been this effect is because of interaction with the enzymes. So to understand this, so we combined several methods from modeling, enzyme engineering, and biophysical characterization to understand the interactions in this complex system and also to improve it later. So as I mentioned, modern detergents are very complex. So some of them up to above 20 different ingredients. And as you see here, I show the most important ingredient that we have used. So in principle, we decided to focus on the main ingredient in the complex wash detergent. So as you see, there are surfactant, polymer, which are used in different, and for example, as surfactant, we use mainly 2 anionic surfactant and surfactant are very important in detergent formulation. And as polymer, we use 2 polyelectrolyte, which one of them is a renewable resources, so-called PGA, and one which is PAA. And we showed that both of them might have effect on the boosting. As you see, so one of the third important ingredient is enzyme. So, and as I mentioned in the introduction, so the most important enzyme in the detergent are proteases. The proteases are used in order to remove the protein-based stains. And just short, what are the proteases? Proteases are enzymes which belong to the hydrolases. So in principle, they can digest polypeptide chain. So the protease that we use here, I do not go too much to the detail, but as a main structural feature, they have 5 residues, including catalytic triad and an oxygen anion hole, which they can digest a peptide in the protein. But you will hear from me in the talk that there are 2 important calcium binding sites, which are important for the structure of these proteases. So in principle, this is the proteases that we use in our studies. But to study the interaction, as I mentioned, the system is too complex. We decided first to look at the interaction between the 2 systems, and then further we try to increase the complexity of the system. So we started with a study of the protease surfactant, then we look at the protease polymer, surfactant polymer, and then all the system together with this numbering scheme. So here you see exactly how we look at the system. So let's start with our modeling. As you see, we are talking about system which is very complex. So we could not use mostly atomistic simulation, but during the project, you see when you are working with the protein, you also need to know exactly which amino acid you wanted to use for engineering. That's why we use two level of simulation. So all atom, molecular dynamic, and coarse grain simulation. I mean, you can imagine that with system, including surfactant, we have surfactant method to simulate. That's why it's much faster to use the so-called more coarse grain model. But what is the scheme for this modeling? In principle, so we develop first all atom, and then later we used Martini method to scheme to derive our force field parameters for modeling this system. And what we did, we first parameterize the system using all atom simulation against our experiment, and further we develop Martini for larger system. For example, we use mainly Martini modeling and simulation. So first we simulated every system separately. Later we, for example, for binary system, we used Martini or all atom depending on the complexity of system for our modeling. But later, as you see, so for our simulation, we have repeated this in 2 different conditions, which I come to that later. So we use simulation in the presence and absence of doubly charged ion, including a calcium 2+. So in principle, as you see in this scheme, we benchmark our system against experiment. We develop all atom. Later, we use the all atom to drive our coarse grain modeling, and then we use this for simulation. But here you see the coarse grain scheme. It's a standard 4-to-1 mapping mainly. As much as possible, we use the Martini force field. So here you see that the 3 surfactants that are used in our study, and also for polymer. So we use the same scheme in order to drive our coarse grain model. But let's start with the first result. So as I mentioned, we observed a boosting of an enzyme and in this complex detergent. To understand the effect, first we look at the enzyme activity. As we know, protease is an enzyme which can digest a peptide, and this is the assay that we used. But as you see here, when you look at enzyme activity in the presence of surfactant, so you see that enzyme activity is lost. This is known because surfactants are mainly denaturing proteins. But interestingly, we see that when we look at the removal of stain from a surface, not in the solution, we see that we have much more solubility performance or cleaning effect in the presence of surfactant. And this effect is more than additive effect if you sum up the effect of the protease and surfactant separately. So we think that this is a synergistic solubilization from the stain of the cotton. So here I show you, so we were wondering what might be the reason. So we did the molecular dynamic. I hope I can show the movie here, but unfortunately it's not possible, it seems. So, but we performed all atom and also a coarse-grained molecular dynamics simulation between the protease and surfactant micelle. And as you see here, so we observe that our protease is complex with 4 micelle from the surfactant. This result were further confirmed using dynamic light scattering. So, and what is interesting is that this complexation, when you look at CD spectra explain you if the protein structure because of the interaction is changed or not. So as you see, the CD spectra of this protein in the presence of the surfactant is not changed. So we do not expect any change in the structure of the protein or any, let's say, significant denaturation of the protein. So we see the boosting of enzyme in the presence of surfactant, and we see the complexation. So we believe that this might be the potential reason. So I mentioned that we did also all atom simulation, so or coarse-grained simulation of the protease and surfactant. So as you see here, so we did it for 2 surfactant, both negative charge. And what we see that there are certain residues or amino acids on the surface of the protein which are interacting mainly with a surfactant. So in order to validate this result and also to see the effect of the changes, so we identified the position which are involved in the interaction, shown here with this heat map. As you see, these are the amino acid on the surface mainly of the protein, and mainly these positions are close to the calcium binding site of the protein. So we identified this position, and then further we subjected them to site saturation mutagenesis. So what does this mean? This means that we exchange every amino acid in this position with 19 other amino acid, natural amino acid, to see the effect. So as I said, these hotspots were targeted, and then we identified new enzyme variant using our assay. So here you see the result for the anionic surfactant SLES and then MES. And as you see clearly, so this is the wild type enzyme without any changes, and these are the mutation we generated. As you see here, so we have obtained enzyme variant, which they have much more performance in the presence of surfactant, and we have identified up to 190% improved if you see for some variant. But what was also interesting for us, when we use this variant and to put them in a complex function matrix, as you see here with the complex, we see also still we have identified variant which have up to 40% improvement in such a complex system. Then this shows that we have identified the position which are involved in the interaction, and we have also improved the protease performance in the presence of this surfactant. So then now let's look at the second system. So as I mentioned, the second system is protease polymer. So we titrated our system. So we, as I said, we had the protease and surfactant, and then we tried to increase the concentration of one of the polymer. So as you see here, for 2 surfactant, we see that in the presence of polymer, we have much more cleanness on the cotton. And interestingly, when we look at different assays, so we can use a very simple peptide, which will not be the representative of the final application in laundry, a soluble assay, and an assay which is much more representative in the presence of the cotton. So this means that is a protein stain which can be removed by proteases in real laundry. So you see that the effect of the enzyme and the polymer are not additive, but also here, also we see some sort of synergistic effect. So we have much more performance in the presence of both systems. So, and you see here, in the presence of this, we have up to 200% increase of protease performance, for example, for a complex protein. So to understand why protease and polymer behave like this, we perform several experimental techniques. I will not go to the detail, but in principle, for example, we use so-called fluorescence correlation spectroscopy. So in this method, you can look at diffusion coefficient of for example, the enzyme, which is labeled. And as you see here, so we see that in the presence of the polymer, we have increased hydrodynamic radius. So this means that the protease and polymer are complex to each other. And of course, to understand the thermodynamic behind it, we performed so-called isothermal titration calorimetry. And what do you see? So in principle, as you see in this model, we see that after complexation, so we have the desolvation of the polymer. And this process is in principle accompanied by heat release. It's an entalpic interaction, and the binding of these two moiety together is controlled by electrostatic force and hydrogen bond between the protein and the polymers. So further, to validate this result, we also perform molecular dynamic in all atom and coarse grain simulation. And interestingly, you see here for both polymer, we see that both polymer are also interacting with the surface of the protein, more or less in a similar mode of binding, close to these two calcium binding site of this enzyme. And so to validate this result, we also identified some position, as you see here, near to this calcium binding site, and we again subjected them to so-called site saturation mutagenesis. So this means that we exchange this amino acid with 19 other amino acid So, and interestingly, what do you see here is that comparison of the generated variant compared to the wild type. And as you see here, so we see that by mutation, we also identified variants which have higher performance in the presence of PAA or surfactant, and we could improve it up to 300%. So interestingly, this effect is present for both use polymer or polyelectrolyte. The effect is stronger, for example, for PAA, but there are a lot of optimization also possible in terms of size of the polymer and charge, and I'm not going to that details. But as you see here, so we improve this, and then later we see that we have also the same, even to improve this in the presence of also very complex detergent. So up to 60% increase of performance we have identified when we use this variant in a complex wash detergent. So the next system is surfactant and polymer as the main ingredient of detergent. So we look at effect of interaction between surfactant and polymer in two different conditions of the water. As you know, water might have some ions, which we call it water hardness or softness. And here we use 2 different degrees of water hardness, 15 degree and 0 degree. And as you see here, it's very interesting to see that the effect of the cleanness of these two systems is much more when we use a hard water. This is opposite to the general common knowledge that you can wash, for example, or washing is better in soft water. But interestingly, what we see when we look at our solubilization efficiency, as you see here, we look at the surfactant concentration and the cleanness. So we see that cleanness is mainly possible when we have the surfactant micelle, so above their critical micelle concentration. And what is very interesting is that when we add the PAA, so we see that this effect of improvement of solubility is much pronounced when we have hard water. And this is, as you see here, so we do not have any change in the presence of the polymer. So this was very surprising us, because in this system, so we have a negatively charged surfactant and negatively charged polymers. So we do not expect that this similar charge moiety they could interact, but based on our molecular simulation, we see that, of course, this is the case. So when you have a 0 degree water hardness, we do not see any interaction between the surfactant and polymer, but we see a complexation of surfactant and polymer in the presence of this hard water. And here you see the distance between these two moiety, and this result further confirmed by using dynamic light scattering. So based on this, we propose that we also have a kind of unanticipated electrostatic attractive interaction between two similarly charged surfactant and polymer, and they form some sort of nanoreactor. This nanoreactor might be responsible for higher solubility and increase of also the efficiency. So now, after studying every single system, so we look at also 3 systems. So for that, you see here the result of cleaning. As you see here, so when we have the polymer or surfactant alone, we have some cleaning, but when we use the combination, for example, of these two with high water hardness, we have improved solubility, but the effect in the presence of the protease is really improved, and we see a synergistic effect of this ingredient together. And to understand this, so this as you see here, so we performed also a coarse-grain simulation of all the system, and surprisingly, what we see is that when we do not have any ion in our system, we do not see the assembly of this system. But when we combine this in the presence of the calcium, so we see that we have a high assembly of these three systems together. And as you see in this model, so we see that surfactant and polymer, before they can interact through bridging through calcium, and they can interact with the calcium binding site of the proteases. But this will not be the case when especially we do not see much clustering of those in our coarse-grain simulation. So now let's look at all the system together. So based on this combined experimental and modeling studies, so we provided a model for detergent, as you see here. So in this system, so we have interaction between the polymer and surfactant through calcium bridging, and we see also in our simulation that this negative charge, they can also interact with the stain on a cotton, so-called CO3 stain. And we see that also protease and polymer, as we said, and surfactant, they compete in interaction with the calcium bond site of the proteases. So based on this, that brings me to the lesson that we learned from this. As you see, so we could increase the performance and sustainability. So here I do not show the number, but we could increase up to 250. So this is a very important progress in the development of so-called condensed formulation of detergent. And I hope that I was able to convince you that enzyme engineering is a robust and rapidly advanced technology to tailor enzyme, even for very complex and harsh formulation. So so it was very also for us surprising to see that we could combine rational design, direct evolution, and also several experimental bioviscosity techniques to understand the interactions between such a complex system, including proteases, surfactant, and polymers. And in the end, we also generated some hypotheses regarding this large assembly of protease, surfactant, polymer, which they had high and superior solubility performance. And with that, I would like to thank all my colleagues. So this work was done at my former institution, RWTH Aachen University, and in cooperation with the Henkel R&D department. And I would like to thank you all for attention. I would happy to take questions.
Thank you very much for such an interesting talk. We already have some questions in the chat that I'll read out. The first question is from Stefan. Considering the interaction spots between the protease and micelles, can the protein be considered as a patchy colloid? And if so, is this protein-protein aggregation a relevant factor for detergent performance?
I mean, we do not expect aggregation, and by that means, so what was very interesting or surprising for us was that we see every protease is complex with 4 surfactant micelle, which is confirmed mainly by dynamic and static light scattering, and we believe that this assembly together improve the exposure to the surface of the cotton, which they improve but we do not have a large aggregation of many, let's say, surfactant, and we do not observe any denaturation of the enzyme.
Thanks. And we have a second question from Rax. What tools do you use to generate the parameters for Martini force field, and how do you evaluate the correctness for the mesoscale force field?
Okay, so I think I was maybe I misunderstood. I was confusing, I guess. So we didn't develop any mesoscale technique. So we develop all atom model. We also develop Martini, and we use a standard Martini force field, but for proteins. This is a standard amber, this standard Martini, but for the others, we drive the parameter based on the Martini, let's say, Bible, like the table that you have, the 4-to-1, and try to find the best or fitting bead, perform the simulation, compare it with the all atom, and also compare with the experimental data. So this was our approach to do it.
Thank you. And we've just had one final question from KMBA. have the complexes with my cells been seen with other enzyme classes, such as lipases?
We have observed this only for 2 enzyme classes, mainly the one that have such a calcium binding site, but not for lipase. They do not share the same structure feature. So
Great.
we mainly see for protease and the one that they have a calcium binding site.
Okay. Thank you very much. And they say thank you as well. And I guess perfect timing as it's 2 o'clock, so we'll move on to our next speaker. Thank you again very much.
Welcome. Thank you.
So our next speaker is Professor Ken Lutus from the University of Warwick and Lutus Science and Technology Limited. And he's going to be speaking on energetic material formulations, the quest to bridge the gap between atomic and macro scale by simulation.
Hello, can you hear me okay?
Yes, I can hear you and I can see you.
I will just try to share the screen.
Yeah.
Is that okay?
Yep, I can see your screen. Yep, and now it's in presentation mode. Perfect.
Great. Well, thank you for the invitation. The title of this is Energetic Material Formulations, as you can see. The subtitle is The Quest to Bridge the Gap Between Atomistic and Macro Scales. I'll give you a brief resume of that, if you like, but obviously we can't concentrate on all of that today. The co-authors here, I'm sort of the experimentalist here. Rick Anderson and David Bray are the main computational guys, and we've been working together for many years on this, and certainly couldn't do it without them. They're in the Hartree Centre, and if you like, I'm a bridge between the Hartree Centre and the world of energetics. And there, I've been working with the Falcon project for a number of years, and now I work ever so closely with them. And I'll say a little bit more about them later. The picture there is from our centre. This is a static firing of a rocket motor using the materials that I'll talk about today. This is based at Westcott, very close by to where we are now, and the idea is to solve problems here and improve the systems. Anyway, I know a few of you know about the rocket motors. I guess most of you don't. So what I thought I'd do is give you a quick overview here. And this here, the presentation here, just summarizes the 3 types of rockets. One is liquid. This uses a pressurized liquid fuel and a pressurized liquid oxidizer, and it pumps those into the nozzle and ignites them. And this is what you saw with those things like the launch of the space shuttle. The big orange vessel contains the liquids, and then the motor is here. But it also has solid rocket boosters. And you all remember those. These are jettisoned. And these are a composite of solid fuel and solid oxidizer in a solid mixture. And then there's the hybrid rocket, which uses pressurized liquid as an oxidizer into a solid fuel. Now, each one has advantages and disadvantages. The solid one that I'm going to talk about today is, if you like, the more robust, the simplest, and it has one big disadvantage. And the big disadvantage is once it's started, you don't stop it. So this is a cutout here of the solid rocket motor. It has a gap down the middle. The propellants on either side, if you like, in the cylinder. It has an igniter at the end and a throat to adjust the pressure. and then it's ignited, and then it's off. I'll give you an example of the components here. It has an oxidizer, energetic crystals such as ammonium perchlorate. It has a fuel. An example there is aluminium metal. Now, mixing these things is not easy, and they have processing agents. One of them is a plasticizer, which I'll talk today about. It's all held together by a continuous phase, which is a polymeric binder. There are a number of these, but what I'm going to talk about today is hydroxy-terminated polybutadiene. So that gives you what's in there. This gives you an idea of the amount in weight of a simple solid rocket motor. You see, most of it is the oxidizer, and the more you can put in there, the better it is. The binder here, I put about 15% as the polybutadiene. We'd like to go lower than that. Then you have a fuel, the processing aids. The polybutadiene is cured, it's cross-linked. And you have a cross-linking agent in there, which actually, it is a rubber. So that fixes the rubber in the rocket structure. And then you have things like burning rate modifiers in there. So I entered this field not so long ago, and there were existing problems and a need to improve things. So as I've done quite often, we tried this, not tried, this is fundamental. You know, you have a theory, you do the experiment, and the idea is that each time we do the experiment, we try and do the simulation. Each time we get the results of the simulation, we justify that with experiment. You know, that's the way we've done this over the last few years. And the idea was to look into simulations at all length scales. And if we go on to the next slide, this gives you an idea of what we've been doing in terms of the length scales and the probe methods you can see. We have gone from the complete atomistic level. We've gone up, if you like, atomistically in scale, but we've also used coarse graining. We've done a lot of dissipated particle dynamics on this, and we're getting some really good results. We're also fortunate to have the ability with the Hartree Center to go into this exascale computing, so we can actually form really large molecules atomistically as well. So the idea being is that we want to see how the molecules react together, physically that is, and also chemically. But then we want to see how these are mixed, and then they behave differently, if you like, once they're cured on that. A lot of fluid dynamics, computational fluid dynamics is being done. We've taken a slightly different approach because what we wanted to do was to look at different mixing methods. So we've used Lattice-Boltzmann methods to look at the particle movement. And then later on, although we've only done a small amount of this, we've used smooth particle hydrodynamics to look at the behavior in the later stages of mixing. So why would we want to do this? So you see one picture there of conventional mixing, and basically this involves blades rotating. And one of the things that I don't want to be close to is mixing energetic materials with rotating blades. Anyway, this is the conventional way of doing it. Recently, we've been using resonant acoustic mixing, and that's the picture on the bottom. This is really useful for highly filled composites of high viscosity media, and hence we've been looking at the different stages of this mixing, the wetting of the particles, then the percolation of the materials, etc. So the picture on the right, I actually took that in 2009 when STS-125 Atlantis took off. I was lucky enough to be there. And that was before I worked on this stuff, and never did I imagine that I'd actually be working on some of these materials. However, in 20 minutes, I can't cover all this. What I'm going to start is at the atomistic level to talk about how these materials interact and what are the differences between them. So what do they look like? So we've done a lot of X-ray tomography of inerts, but also live propellants. The two pictures there, one is a sample, a rectangle cutout of a live propellant. And the one on the right is from a much larger sample, but a circular cross-section cut out mathematically of this. And the particles are supposed to be spheres, and as you can see, they're not. But there are many, many things that we needed to look at here in terms of trying to make improvements. One was adhesion, the binder to the particles in there, the mechanical properties, of course, because these things have to suffer large amounts of vibration. And then there's the problems. You put in a processing aid, and then sometimes the processing aid in operation creates problems. And this is what's happening with the plasticizer. The safety and efficiency on this, obviously safety is a major concern. Then there's the curing and cross-linking. You know, what happens when you cross-link these materials? Can you make it better? What happens when the polymer shrinks? And also the ability to increase the energetic content is, especially nowadays, quite a big thing. So I'll give you an example here. I'll take the example of the plasticizer that's put into processing. Typically, dioctyl adipate is used. You can use other ones. You can process it. It's very difficult to process without this. However, it has problems. It likes associating with the cross-linking agent more than anything else. It's not completely compatible with the polymer binder. It tends to migrate out of the binder. And if you like, you can see this in other areas. If ever you've looked at a label, you know, stuck on with the pressure-sensitive adhesive, after a few years, you can see the oil that's put in a pressure-sensitive adhesive migrating out and even through the paper. Or even if you have something like a kitchen implement or something like that, that's been over-molded with the rubber. And a few years later, it becomes sticky. And this is because they formulate the rubber with the processing oil. And this slowly comes out over time. And I'm pleased to say, by looking at this scientifically, we've actually invented a new resin here that we can put into these things, which doesn't have these drawbacks. So if we keep on with this problem here, this is an X-ray tomograph, and you can see the ammonium perchlorate particles in the propellant, but also the binder here. And the situation is we can see differences in density of the binders. And with other methods, we've seen what this is. And this is due to the plasticizer migrating over time and forming its own little pockets in there. This is a model, the top one of the plasticizer, the dioctyl adipate. The new resins, we adjust the polarity. And in this case, we are adding an aromatic link in a stiff backbone. Actually, the backbone is dicyclopentadiene based. And to give you an idea of the sizes here, I hope you can see this. So the top is, if you like, the pre-polymer. This is the hydroxy-terminated polybutadiene, molecular weight of about 3,000, hydroxyl functionality of about 2.5 per molecule. And if we expand that window, you can see the relative sizes. There's two plasticizers there, the new resin, and also the cross-linking agent, to give you an idea of the sizes. So with the molecular dynamics, we looked at that in detail. We looked at the mean square displacement measurements. This is quite a good summary because this is at the end of about, I think, 100 nanoseconds. And the one on the left is the plasticizer. It was completely random in terms of the distribution. The gray is the polymer, the red is the plasticizer, and you can actually visually see, as well as numerically see, how this migration takes place. Whereas the new resin remains completely dispersed. We even went one step further, and we looked at a simulation experiment splitting them up. And after a computationally infinite amount of time, these remain the same, which means they really don't want to mix. Whereas we don't get this problem with the new materials. So I said, you know, we want to look at how they interact with themselves and each other's. One interesting thing that we found here is the hydroxyls, not unsurprisingly, want to associate. And here you can see a few polybutadiene molecules, and the hydroxyls want to associate at the end. And if there's any water present, this exacerbates it, of course. So these are the curves, and as you can see, this gives you the number of molecules, i.e. the hydroxyls, in a cluster versus time. And they want to, if you like, slowly start increasing to about 4 hydroxyls. This is a bit busy, this, but I'll try and take you through it slowly. The top 4 images here are with the plasticizer and the polymer, and the bottom is with the newer resins. So these are atomistic, and this is using radial distributions. And basically, the closer you get to 1 here, means the better it is. The more it deviates, the more it wants to aggregate and phase separate. And the colors determine the time. So as you see with the plasticizer, the blue is the longest here, and it wants to aggregate together, whereas the resin beautifully goes to 1 here. We put in the hydroxyls association here as well with the polymer, and as you can see, you get many alone, of course, but then you get this this peak of association here as well. So how would I summarize this? It's important to look at the hydrogen bonding of these terminal hydroxyls. The plasticizer shows increasing self-aggregation with time. We can actually improve the plasticizer, but the best plasticizer doesn't exist commercially yet. And in fact, I wouldn't go that way because the new resins actually improve the physical properties as well. And the effects of these different formulations on the diffusion of the components is important, because the plasticizer likes to link with the cross-linking agent as well, and therefore you lengthen the time for curing the propellant. And to give you an idea of the improvements, these are graphs. This is percent improvement, is when you make up a traditional blend with a plasticizer and you make it up with the new resin. And this is a stress strain, and so the maximum stress is considerably increased with the new formulation and also the strain. So if you like, this is akin to the best ways of formulating an adhesive for various applications as well, which is an area that I've spent many, many years in. So as a quick run through of this, we've, as I said, we've been lucky enough to transfer this to much larger scales, because one of the key things I wanted to do was to see if we could look at cavitation. Most failures occur through cavitation. Where do they occur, etc. So we did these stress strain measurements on the computer. And here you see on the right, the effect of stretching these molecules. This is atomistically. We're aiming to do this with coarse grain as well. And to look at the first nanoscale failures here. And as you can see, we've got not bad results for a very, very first try here. So we're going to extend these and hopefully start round about now. And because of the commercial aspects of this, we haven't published much of this. This has been presented scientifically, if you like. But in terms of the coarse graining, we have published 2 general publications. One of them was which is in the abstract. So I just wanted to show you this. I actually don't have a good video of the stretching and cavitation. So this is a handheld one, but it really shows the difference. So a conventional binder, if you like, is on the left. And if I stretch that, literally I stretch it, this is my hand doing the stretching, something interesting happens. So you get the cavitation taking place throughout. If we look at the modified binder, which is fascinating, we do the same thing. There was a bubble in there, but we don't see the cavitation, or the cavitation is too small. So that's a brief demonstration of linking the simulations, the molecules, etc., to make the improvements. And finally, I'd like to thank everybody here. There's Daniel Jubb and the Falcon team. These guys are tremendous. They are the best company I've ever experienced to work with and for. Michael Seaton from the Hartree Centre, he did the lattice-Boltzmann methods, which we haven't discussed, and the exascale stuff by Seddon and Guadalupe as well. Very many thanks to the various departments of MOD. We're doing this for to help the country, help the UK here as well, and we work very closely, and it's been a pleasure working with those. The cross-linking in the rheology, which we haven't covered, at the University of Oxford. Looking at the diffusion experiments, like mean square displacements, we tied that in with the University of Greenwich. And finally, the tomography work was done at the Diamond Light Source and the University of Manchester. So I've raced through that. I apologize for the speed, but it's difficult covering such a wide area on this.
Thank you very much. That was very interesting. We had some questions in the chat already, and I have some for myself as well. So Robert asked, what force fields did you use? Were they published ones, or were they developed specifically for this application?
I'm sorry, could you repeat it?
Sorry. What force fields did you use, and were they developed ones, or were they developed specifically for this application?
No, they weren't developed for this application. We used a number of force fields on this. Oh, I'm trying to think which ones we used. I'll try and remember in a minute. Anyway.
Yeah. And we have a second question from Rax, which is, how do you generate the cross-link structures? Have you written an in-house code to do it?
Can I just turn my speaker up just to so I can hear you a little bit better? Can you try again?
Can you hear me now?
Oh, brilliant. Yeah, sorry about
Questions
that.
are in the chat as well if you want to read them, if that helps. So how do you generate the cross-linking structures, writing in-house code?
An excellent question. So we've done most of the work here on uncross-linked material. So this has been mainly due to this first stage in terms of mixing. So we want to look in detail at the most efficient way we can mix these together. In terms of generating the cross-linking, what the guys at Hartree have done is we have the cross-linking points on that, and they have generated the the total matrix with their own code, if you like. I'm not sure whether it's got a name or not. We'd have to ask them in order to create. We can cross-link completely. So each polymer molecule has at least 2 hydroxyls at the end, but some of them have, half of them have a hydroxyl somewhere along the chain. So that question is one that we'll be addressing very, very soon. So we can either cross-link completely through their own code, or, as is often done, we don't do it completely. And it's interesting to see how the two differ. Now, one of the things we want to do, and we haven't done yet, is actually look at the molecular weight distributions here. So we haven't gone to any great lengths sort of refining the cross-linking until we then refine the molecular weight distributions and what happens there, if you like. So it's that bit's work in progress. But as I say, it's they've written their own code to do that.
We have another question from Peter. Maybe you hinted at it, but it might be possible to eliminate the plasticizer completely by design of the polymer system. Might the use of Hansen solubility parameters help to simplify formulation compatibility problems?
Right, absolutely. And you look at some of their examples, and we've done exactly that. So in other words, if you look at the adhesive industry, you can look at, you get a polymer, a rubber, and you put in a tackifier in there in many cases. However, if you look at the polymer microstructure, the architecture controls the rheology of that. So if you can do that, which we have done in the past in other systems, then you can actually do exactly what Peter said. I think it was Peter said.
Yeah, it was Peter.
And do that. Now, that, if you like, is a good goal to aim at. It's not easy at the moment to actually do that, because then we have to make another polymer system, and that's a completely different process. As you can imagine, this industry is a very conservative one, and rightly so, I think. And what we've got is we've got a tried and tested method of improving adhesion, mechanical properties, tensiles, etc., which we are aiming at first. So the quick answer is, I'm sure if we spent enough time, we could do that suggestion. Whether we have time enough in the near future to do that, I don't know. Good question.
Great. I have one very quick question for myself. The tensile tests that you showed, were they for cross-linked systems or were they uncross-linked systems?
Oh, cross-linked.
They were cross-linked, yes. Yeah. Okay.
Yeah, cross-linked. And the other bit which I haven't put in there, I talked about safety, longevity, etc., as some of the things we want to do. The beauty of these resins is that they actually improve barrier properties as well. So water and oxygen. So the materials with these resins in last much longer than anything else. They degrade much slower. they suffer from much less oxidation as well. So that's one of the other advantages on that.
Great. Thank you very much. Peter also says thanks in the chat. And with that perfect timing again, we'll move on to the third and final speaker in this section, and that's Dr. Joe Peterson from the University of Cambridge. Unfortunately, Joe can't be with us today because he's in the process of moving to UCLA, and I think he's actually on the plane as we speak. So luckily for us, he knew this and he sent us a video, which I think Phil has loaded and you should all be able to see. And he's going to play it now, the pre-recorded talk. Oh, we haven't got any sound.
Let's try again.
Yeah.
Hi, my name is Joe Peterson. I'm a postdoc with Mike Cates at the University of Cambridge, and I'm giving a talk on population balances for full chain constitutive models of living polymers. So what are living polymers? Living polymers are systems of polymers where the polymerization reactions are reversible, therefore non-terminating and said to be alive at all times. These living polymers are often formed of self-assembled type structures where the forces or energies holding the chains together are on the order of, say, 10 kT. Worm-like micelles are a particularly industrially relevant platform for living polymers because when you want to deliver surfactants in a given application, whether it's shampoo or enhanced oil recovery, worm-like micelles give you a great opportunity to tune the rheological properties of the fluid to add value. Nobody wants a runny shampoo, for example. So what is the rheology of living polymers like, and how is it different from the rheology of covalently bonded polymers, for example? We'll discuss this in terms of the linear rheology and the nonlinear rheology. So in the linear rheology, for example, if you plot the storage modulus and loss modulus parametrically, you get this semicircular shape for certain formulation spaces that's indicative of a material with a single relaxation time, which is surprising because worm-like micelles have a spectrum of lengths. You'd think they would have a spectrum of relaxation times, but these formulations evidently don't. In the nonlinear rheology, you can also get shear banding instabilities. So we'll talk a bit about both of these here, but first let's look at the linear rheology. So the theory for linear rheology of worm-like micelles goes back to work by Mike Cates in the late 80s. And the idea there was that all you had to do was combine the existing reptation model with a reversible scission reaction picture, and you would exactly reproduce this single relaxation time phenomena if you were in the so-called fast breaking limit. The idea is that the chains break apart faster than they're able to natively relax their stress. And in that limit, you recover a single relaxation time and a scaling of that relaxation time that goes as zeta to the 1/2. Okay. Now, there have been follow-up work in this area that extended it from not just being reptation, but also adding contour length fluctuations and double reptation. But it's always been constrained to linear rheology. There have been some nonlinear rheology models for worm-like micelles, but they never take into account the same level of detail for the stress relaxation coupled to polymerization reactions. It's always at a more abstract level, right? Where it's been, the models have been developed largely by intuition and not in a systematic way from a reliable microscopic picture. Okay. So in today's talk, we'd like to change that. We would like to take the level of microscopic detail in the original Cates theory and scale that up to, for example, nonlinear rheology models. This talk is mostly going to focus on linear rheology just as a means of developing the framework. But once you develop the framework, it's more or less trivial to extend it to nonlinear rheology models. Okay, so the first thing that we need to look to is population balance equations for the number density of chains within a given length interval. So the idea is you bin up the molecular weight distribution into different length intervals, and you look at the different reaction pathways that are available to the polymers, and you describe how material is moved from one bin to another via these different reaction pathways. And here we're mostly going to look at reversible scission. But the material itself, the mass, is not the only interesting thing that's moved around to different bins during these reactions. You also have a distribution of surviving tube segments, for example, that gets moved around. So the idea is that if you have chains 1 and 2 combining together to make chain 3, or the reverse process, chain 3 breaking apart to make chains 1 and 2, if you know the tube survival profile, right, the distribution of surviving tube segments, unrelaxed tube segments in the reactant chain, you can figure out the distribution of surviving tube segments in the product chains. So you can figure out how reactions move unrelaxed tube segments through the molecular weight distribution and to different contour positions and so on. And you can write this out as an evolution equation. If you have the normal diffusion equation that corresponds to the rotation model for stress relaxation processes, all it ends up being is an added set of population balance terms appended to the end of that, and those terms scale inversely with the breaking time, for example. And you also have initial conditions and boundary conditions to worry about that show that all the chains are unrelaxed at the initial condition and that chain ends are always stress-free. Okay, so the advantages of this over the models that were done in the late 80s and early 90s is that this approach is systematic. There's no intuition needed. It is detailed in that it gives you the full picture of tube survival profiles at all molecular weights, all contour positions, gives you more information than just the bulk rheology, and that ends up being useful. You should see my other talk for more discussion on that. And the framework is extensible. This is not in any way limited to reptation. As we'll show later, we can look at contour length fluctuations, we can look at double reptation, we can look at chain retraction, convective constraint release, whatever you want, if you have a PDE model for stress relaxation in unbreaking polymers. And if you have a rule for how structural information is conserved during the course of a reaction, then you can write out an evolution equation for the living polymer version of the unbreaking system rather easily. Okay. So as a test case for this modeling framework, we're going to look at the fast breaking limit that Mike Cates studied back in the late 80s, and we're going to affirm that our modeling approach is able to capture the right results. So the first thing that we do, we take the fast breaking limit, tau b is going to be very small. The reaction terms to leading order dominate our evolution equation, which means basically that the surviving tube segments are being shuffled around through the molecular weight distribution to different contour positions without any meaningful amount of stress relaxation taking place. And as a result, the tube survival probability is, to leading order, uniform at all contour positions and all molecular weights. Problem with that is that violates our boundary conditions. The ends need to be stress-free, which brings about a boundary condition. So in order to look at the boundary layer solution, you do this rescaling in the contour variable S, right? With the smaller your value of zeta, the faster breaking the system is, the closer and closer to the chain end you need to resolve the stress relaxation process, right? So we're not going to discuss the solution to that, the detailed solution to that boundary layer, but what we can show is that if you return to the full governing equations for the tube survival equation, and you integrate over the molecular weight distribution, you integrate over all contour positions, the first thing that happens is all of the population balance terms drop out because those are conservative. And the remaining term, you can go in with the results from the boundary layer analysis and show just from that, that the tube survival probability, the average tube survival probability decays as a single exponential with a relaxation time that is the geometric mean of the typical reptation time and the typical breaking time. So it recovers the results from the Cates model without any need for intuition. It just relies on tools of asymptotic analysis and boundary layer analysis and so on. So it's pretty powerful. Okay, but more than that, it's trivial to extend the original equations to add new stress relaxation processes. So, for example, you can look at contour length fluctuations by adding in a diffusion coefficient whose rate of diffusion is dependent on the contour position. So the closer you are to the chain ends, the faster this diffusion process is able to occur. You can add in double reptation by basically indexing each tube segment, not only by its position along its own contour, but also by the contour position of the chain with which it is co-entangled, the size of the chain with which it is co-entangled. And then you have stress relaxation from one, stress relaxation from the other chain, and the reaction processes added in as well. Finally, you could look at stress relaxation. So where lambda is the stretch at a given contour position, you can do the same thing and look at how living polymer reactions change the stretch relaxation processes in a system of polymers. So that's great. But the really big deal is that we can go to nonlinear rheology as well. And in nonlinear rheology, you need to worry more than about just the tube survival probability, right? You need to worry about what's called a tangent correlation tensor. This sort of tangent correlation tensor approach was first introduced by Milner, McLeish, and Lichtman, and was subsequently improved to the so-called GLAM model. The idea is that if you know the tangent correlation tensor, which is represented as this, square piece of information, if you know the tangent correlation tensor for one chain, for a chain, for two chains that are coming together, you can figure out the tangent correlation tensor for the product chain. And then once you've done that, if you're interested in the fast breaking limit, you can do the same kind of asymptotic analysis and boundary layer analysis that we put together for the reptation case, and you come up with a dramatically simplified constitutive model that can be effectively solved with excellent accuracy in as few as 6 modes. And so it's totally suitable for CFD applications. And you haven't lost any of the underlying physics. You still have the full picture for reptation, retraction, convective constraint release, and reactions at the core of the model. And all of the simplification steps have been done not by intuition, but by systematic use of asymptotic methods and boundary layer analysis and so on. Okay, so to summarize, the idea is that we were able to put together a systematic framework for modeling the rheology of reacting polymers. You start from population balance equations that describe how material is advected through the molecular weight distribution by reactions. And then you start thinking about what else is advected along with the material. In this case, it was the tube survival probability for linear rheology. For nonlinear rheology, it was the full information in the tangent correlation tensor. And in future work, we hope to be able to extend this to branch structures. And we'd also like to look at improvements to the way that constraint release terms, convective constraint release, thermal constraint release, are modeled in things like the GLAM model, because the way it's done currently may have a number of problems. So if you're interested in practical tools outside of the fast breaking limit, this talk took a particular interest in the fast breaking limit, where these asymptotic tools and the boundary layer methods work really nicely. But if you're interested in those other tools, I would encourage you to come and see my other talk as well. Okay, so with that, I'd like to acknowledge my advisors, Mike Cates, Gary Leal, as well as collaborators on this project, Junju Mu, Ian Stott, Daniel Reed, and the funding from Cafe 4DM and Unilever. With that, I'll take questions if there are any.
Okay. Unfortunately, he can't take questions because this was a different talk. And with that, that brings us to the end of this second session. I'd like to thank again all the speakers, Mehdi, Ken, and Joe. And we have a break now, so I'll see you all back here at 3 o'clock.
Okay, so I think we are ready for the last session of today's meeting. As my name is Stefan Köhler, I'll be moderating this part of the conference. We've heard a lot about machine learning or hints to machine learning in the talks today already, and now we'll focus a bit more on actually applying this to formulation problems. Our first speaker is Dr. Brian Yu from Ferrolabs. And Brian will be presenting on his work on Pareto active learning for in silico polymer design. So I'll hand over to you, Brian.
Okay. Let me just share my screen. Okay. Okay, are you guys seeing the, oops, looks like it's going too far. All right.
Looks good.
Okay. Okay, so thanks for inviting me, Stefan. I just want to preface this talk by mentioning that all of this work was done prior to me joining Ferrolabs. So this was all done at BASF, where I was a computational chemist in my previous role. Okay, guess I'll have to use my mouse. Okay, oops. What is going on? Okay, so I wanted to start this talk with just addressing one of the big challenges I believe is for material scientists today, which is to try to be able to synthesize polymers for a wide variety of compositions, topologies, as well as functionality. And one of the grandstanding challenges, I believe, is being able to tune these polymers based on these types of characteristics for any type of design application at hand. Although today, what I will be presenting is primarily just focusing on a single topology, perhaps the most popular topology, which is the linear copolymers. And specifically, I'll be discussing ways in which we'd like to be able to design linear and random copolymers for any type of product application. Don't know why my computer is doing this. Okay, so when it comes to industrial applications, I just wanted to give scope some brief description about how a material scientist would go about synthesizing polymers in the lab. In general, they'd start off with something like 4 different monomers, or perhaps a selection of monomers. I've just labeled them as A, B, C, and D for simplicity. And by no means do they actually use these types of chemistries. Those are there just for example. They would then go ahead and select some of these monomers, try to synthesize polymers based on specific chain lengths, and then put them into some type of formulation, as you folks here on the call probably already know. And when it comes to molecular properties of these polymers, they'd have to satisfy certain conditions. In the case, or in the project that I was working with at the time, my project partners were interested in designing polymers that behaved as dispersants for automotive coatings-based applications. And so the idea here was to design polymers so that they would adhere onto pigments or pigment surfaces, pigments of which are used in the coloring of paints. And secondly, these polymers would also have to be able to sterically stabilize these pigments in the suspension. So what I mean by that at a fundamental level is these polymers had to repel from one another while adhering onto the surface of the pigment. And in turn, the lab scientists could then be able to design things like paint formulations that could adhere onto the surfaces of walls quite well, or they could do things like tune the optical qualities of the polymer material. Again, by controlling things like the particle size, in which case they can tune the diffraction index or fraction index of their material. So coming back to this just design problem where we have this linear polymer, if I were to potentially look at just a 20-mer copolymer as an example, and just being able to synthesize this polymer with just 4 different monomer types, there's a combinatorial explosion of possible polymers that could be sequenced if I were to be able to synthesize these polymers just by controlling sequence alone. So 20 polymers, as many of you know, is not much of a polymer at all. I'm sure some of you would say this is a oligomer, but this is just a simple proof of concept problem that I wanted to address. So when it comes to computational chemist perspective, the way in which they would go ahead and tackle this problem would be to essentially run high throughput virtual screening. In general, polymers in large companies can be simulated using a supercomputer, and you would, if depending on which type of specific scientific domain you belong to, you would run the type of simulation that would simulate the properties of interest for these polymers. So in my case, when I was back at BASF, what we did was use molecular dynamic simulations to simulate things like the absorption free energies of the polymers onto model pigment surfaces, and then also quantify things like steric stability through metrics such as second virial coefficients. So once we simulated a whole number, generally we'd simulate hundreds, if not thousands of polymers. I mentioned already that for just a 20 mer polymer, you can have 80,000 possible sequences. So this is really just a small fraction of the potential polymers that we can look into. We go ahead and simulate these representative polymers and then try to rank them according to these performance metrics. Once we did so, we can then make these suggestions to the lab scientists to go ahead and synthesize in the lab. And in general, we sort of reiterate these process back and forth, rerun simulations, rank them again, make new suggestions to lab scientists once we got the experimental results. So coming back to this design challenge, what I do want to mention is that running thousands of simulations, well, more than 1,000 simulations, running thousands on the order of 1,000 simulations, even on a supercomputer, was just computationally intractable. I believe at the time when I ran these simulations for some of the project partners, it took roughly 10% of the compute power of our supercomputer for that year. And I definitely got some email complaints saying that I should not be using that much compute power. So yeah, even for me, that like running on the order of 1,000 polymers was just intractable. And so we had to devise new methods into ways in which we could explore this search space for polymer design. So I'm going to switch gears here and just go through the thought process of a machine learning applied scientist or someone who does more of the data science work at a company such as BASF. The way in which they would tackle this problem is to first construct the so-called design matrix or the X matrix, where you would generate your features for all your polymers. Every row for your polymer candidate would represent a unique polymer sequence, and every column would be each of the features of your polymer. So things such as characteristics of polymers that you would use to synthesize the polymer, for instance, monomer type, stoichiometric ratios, the concentration of the monomers, the chain length, as well as characteristics of their sequences. For instance, things like the number of clusters of a monomer type would be one type of feature for that as an example, and so on and so forth. You would add these different types of characteristics that characterize your polymer just at a very basic level, and use that as input columns into your design matrix. You could then plug that into your whatever model that you wanted to test out. Again, this is a regression problem. And then you would actually go about training your model based on your target variables of interest. So in our case, we were interested in these absorption free energies. the second virial coefficient, and thirdly, the radius of gyration of the polymers. So these are sort of proxies into what we believed were molecular thermodynamic driving forces for the application products of interest. Of course, we'd love to just be able to simulate the direct application property, but that was not doable with the models that we had at hand. So in general, it's nice to be able to train machine learning models once you construct your covariate matrix or design matrix, and you have your response matrix as well. You'd want at least a few number, maybe like on the order of 100 points, to at least first train your model. Otherwise, you'd be prone to things like overfitting, or you'd be actually better left off with very simple models such as ordinary least squares regression. So I want to touch upon another sort of technique or a subdomain of machine learning that allows you to train a model with as minimal points as possible, so that you still maximally inform your model. And one of the popular ways in which one could go about doing this is by using a so-called Gaussian process regression model and using the technique known as active learning. So I mentioned Gaussian processes just because it's quite popular in academia. In practice, however, it's not very useful due to the fact that it scales with in cubic order with the number of rows. But for proof of principle, it's a very commonly technique used to study approaches such as this. So the example here I'm showing you that applies Gaussian process active learning is a one-dimensional problem where you start off with a response function. What we're doing is we're training the Gaussian process model using a handful of points as represented with the black points there. And the red point is the points at which we sample our search space iteratively. And after each iteration, we retrain the model. So in this case, this 1D problem, that red point is sampling the point at which the model sees the locale in which you have the highest uncertainty. And so each time it predicts where in which your search space you have the highest uncertainty, and you continuously retrain this. This is, of course, it can be applied without loss of generality to n-dimensional inputs. But when it comes to multiple targets, it starts to become you start to question how well can you sample different points in space, because you might have competing regions of search space that might have high uncertainty for one objective, whereas you might have low uncertainty in that same space for another objective. And so another technique I want to discuss, not so much machine learning based, which is just simple Pareto optimization. So I'm sure many of you have heard of this already. When it comes to materials design problems, Pareto optimization is quite common, or even real world applications. This type of optimization approach is quite popular due to the fact that it recovers the so-called trade-off between your multiple objectives. So what I mean by that is most real world problems don't necessarily have a single overall global solution to their optimization problem. In general, when you try to optimize for one objective, you might end up minimizing for another and vice versa. And so the idea here is to recover the maximal possible for one objective while trading off for another. And so when you do that, you end up with this so-called Pareto frontier. If I have a laser pointer, I know I'm going to need this later. So the red points here is the set of optimal solutions. So Pareto optimal generally has a solution, a set for its solution. This is called the Pareto frontier or the Pareto front. And the red points are the so-called optimal points, whereas the blue points here are your non-optimal. What I want to mention is that this algorithm is purely a classification algorithm. So it scales well for n-dimensional objective problems, and it's very easy to compute. There is no type of vanishing gradient types of problems. We're not computing gradients, so this is gradient free, and it's just a simple classification. Generally, it's done in a pairwise form. Why this is of interest to chemicals companies? For most chemicals companies, what they tend to do is use the same types of chemistries and use them to construct multiple types of products. So for example, when I go back to this coatings applications that I was mentioning earlier in the talk, we might have one product type that might be, say, good for automotive coatings, where it might be quite good in one objective, but bad in the other, where it's less important. But say for coatings that are used in construction materials, such as laminate flooring, perhaps that the second objective is more important, and we'd like to know how to optimize for that second objective. So you can see from a industrial perspective, this is very important due to the fact that you can maximize revenue by recovering this type of trade-off curve. So I wanted to now discuss the algorithm in which leverages both Pareto optimization and active learning. When I discussed this active learning algorithm, I mentioned how difficult it may be to sample search space when you have two different objectives, let alone two objectives that are competing with one another. So just going with this 2D example, what I'm showing you here are predictive means and predictive uncertainties in the shaded regions. And these dark borders here represent the points that were initially used as training. So the way in which one would go about implementing or using this algorithm is they would first try to see whether or not they can recover any sort of Pareto front from their search space using their sort of small initially trained machine learning model. For the points that don't have overlapping uncertainties with any neighboring points in this property space, we can then classify those points as Pareto optimal directly. So some of the points that were used in training for this very simple example turned out to be the Pareto optimal due to the fact that there are no uncertainties that overlap. However, for these two particular points, you can see that there are uncertainties. And for those points, we'd want to focus our attention to, because then we can more efficiently recover this Pareto frontier. And so Pareto active learning essentially allows you to sample those points that are sort of ambiguous and allow you to distinguish this Pareto frontier more efficiently while maintaining a certain level of confidence in your prediction of this front. So this is the basic idea. Instead of just sampling points with highest uncertainties, you end up sampling these the region at which you would predict to be close to the Pareto front. And you do this again in an iterative manner, as I've shown earlier in the sort of video of Gaussian process active learning. So I just want to say that we tested this result as sort of a proof of concept on our dispersant application problem. And in this case, what I'm showing you are all of our polymers that we studied. We ended up simulating properties for 3,200 different polymers. We looked at the radius of gyration, this absorption free energy, and this dimer repulsion free energy to quantify some of these properties of interest for dispersant-based applications. What I'm showing in this figure is all polymers in property space, represented by all the gray points. If you look closely, you can see each of these points represent an individual polymer. The points in magenta are the points that we sampled in the algorithm after initially training a simple model, a simple machine learning model. And again, these are iteratively sampled. So every time we sample a new point in magenta, we then retrain our model. The points in stars are the points that ended up being classified as what we call epsilon Pareto optimal, So this epsilon is just a buffer for how accurate we are with our classification. And the points outlined here are just two-dimensional projections. So here, along with the points outlined in red and in blue, those correspond to all of the same points. Again, these are two-dimensional projections on the 2D planes. And we're just showing for clarity how our classified optimal compares to the true optimal. And you can see that it's not too far off. We are within the error tolerance of our parameter epsilon. So this is just to say that this sort of algorithm works quite well. It helps us simulate things much faster, which leads me to perhaps the key findings. And so here I'm just showing a plot where we are looking at, after each iterations, how well we've classified whether our polymers are Pareto optimal or not. I mentioned we initially started off with roughly 3,000 polymers that we've gone ahead and simulated these molecular properties for. And you can see after roughly 20 to 40, we almost recover 20 to 40 iterations, we almost recover all of the Pareto optimal polymers. Perhaps after 60, we recover all of them, and we're able to discover these polymers. So in total, we only needed to evaluate somewhere within 100 to 200 polymers rather than the entire 3,200. So if we were to compare this to, say, random search, this would approximately equate to 4% of the iterations needed. And so this is much faster than just simply doing random sampling. So all of this work that I just presented is published already. It was published last year. And the code for this algorithm is also available on GitHub, currently maintained by Kevin, who's one of the authors on this work. Okay, so just to conclude, I wanted to mention again, we've only addressed a very small subset of linear copolymer topologies. Not only that, we didn't even look at the entirety of our sequence space. I've only mentioned we've looked at 3,200 different polymers. We did not look at all 80,000, say, polymers for 20-mer copolymer. Again, these are reasons for this is due to the fact that even that type of search space is computationally intractable even with some of these approaches. So I believe there's a lot to explore here. I do want to mention that some of the work that we were continuing to work on was trying to improve our models. So our coarse grain models were more or less limited to n-mers of length 100. We could not go beyond that because then we would have to simulate a much larger system. And so some of the work that we were working on before I left was to try to improve our modeling techniques so that we can access more longer length and time scales for polymer systems, and while maintaining all atomistic resolution information from atomistic systems. And so this was some exciting work led by Nick, who's currently at BSF now. And the idea here was to try to get better models to access longer length and time scales so that we can explore all sorts of topologies of polymers. I think there's also quite a lot to do in terms of the machine learning side of things where we can, rather than featurizing polymers based on sort of higher level properties, we can actually try to featurize them in more of a continuous way, more specifically using things like graph embeddings that can sort of construct these polymers based on their graph structure. I think there's a lot to do there. And finally, I just wanted to discuss there's also improvements that can be made in terms of even the retraining of the model, where sometimes things like bias might end up influencing the model convergence times. And so how, for instance, how you initialize your training could really impact the final results of this type of algorithm. There's also one thing to note also is that we simulated all polymers in our study sort of as a proof of concept, and then simulated this sort of scenario as if we had gone ahead and performed active learning in a live manner. But in practice, it turns out this type of technique is really hard to do. And so there's all sorts of startups that just specialize in ML ops so that you can actually retrain your model without having issues later on. So I think there's also a lot of work to do in this area. So with that, I'd like to acknowledge my colleagues, Kevin, who's currently a PhD student at EPFL, an intern at the time, Gary Prasad, who was also an intern at the time, who's now at Henkel, a colleague at BSF, Shifeng, and Kevin's advisor, Berend at EPFL. And with that, I'm happy to answer any questions.
Okay, thank you, Brian. There are a couple of questions coming up in the chat.
Yep.
I think the first one is from Flor. So she writes, very interesting work. Thank you very much for the presentation. In terms of the polymer adsorption, did you consider the possibility of chemisorption, or is it only physisorption that is relevant in these systems?
Yeah, so to answer your question directly, yeah, it's all physisorption. Most molecular dynamics, unless you're using something like ReactFF, just tend to be physisorption when we run these free energy calculations.
Okay, thank you. Next question is from Paola Carbona, and the question is, thank you, very nice and interesting talk. I did not understand how you reduced the number of polymers to model from the thousands to hundreds. Also, are these polymers solutions or melt?
Good. Yeah, great question. I did forget to mention that the systems that we simulated are in solution. Not only that, the thermodynamic properties that we were simulating was essentially done in infinite dilution. So it's not melt. Yeah, we're making these very, very big assumptions there. When we reduce the number of polymers from thousands to hundreds, what I mean by that is when we initially started off with 3,200 different polymers that we can characterize, with the active learning algorithm, and I might actually answer the next question, we initialize, so had we not simulated all 3,200, the way you would go about doing this is just simulate, say, 100 initially, get all of these properties for that 100, and then iteratively sample your entire search space more smartly. So just try to sample the search space so that you recover that Pareto optimal. And what essentially this figure is showing is that only after 60 more points, so in total, say 160 points, you can evaluate these properties for all 3,200 polymers. I hope that made sense. And so to answer the next question, it's roughly on the order of 100 to 200, or I guess from 100 to 200 polymers that we've used for training.
Okay, thank you. I don't see any more questions in the chat, and we're like 1 minute before time, so I think that's a good point to switch to the next one. Thank you very much, Brian.
Yep, thank you all.
Maybe a quick reminder for all the people still around. I think this is pretty much your last chance to contact Flor Sieberstein if you need a certificate of attendance. So message her in the chat if you need that. And also please think about filling out the feedback form that Phil posted a little while earlier. And with that, we're coming to the last talk today. going from polymers to formulations. Caroline Crowder from Schrödinger will now present us her work on formulation design using combined automated simulations and machine learning. So Caroline, off to you. Can you, you're still muted?
And yes, I should be unmuted now, and I hope my slides are showing.
Yes, perfect.
Okay, perfect, fantastic, thanks. And there's nothing blocked at the top, right?
No, it's just like the white Schrödinger slide.
Perfect, fantastic. Okay, thank you very much for the nice introduction. And then also I want to say thank you for organizing this event and the fantastic talks that we've had so far. So today I'm going to talk about a application case study, at least mainly that is in the field of biosurfactant formulations, where we're trying to combine automated simulation workflows, molecular dynamics workflows, and machine learning approaches. But before jumping into that, I just very briefly like to introduce Schrödinger and also myself. So our company's mission is to transform in a way the way how new medicines and materials are discovered, and we try to do that through developing advanced computational methods. So we are working on developing simulation platforms, digital research platforms, and then also applying those together with our partners and customers. So I myself, I'm leading our applications team for material science within Europe, and so I'm usually located in our Mannheim office. And so the digital approach that I want to talk about a little bit today, and an application study that we are running at the moment in the area of formulations. So I thought that would fit quite well for today. But first of all, so what we're envisioning here, and that's I think come up multiple times today, and also especially in the previous presentation. But a big topic in driving materials research is of course screening large chemical spaces, large material spaces, for optimal solutions. And one traditional way would be to create a structure library using high-throughput simulations, potentially physics-based simulations, quantum mechanics, molecular dynamics, coarse grain, mesoscale, et cetera, up the length scales, and then to select top candidates for the synthesis and maybe reiterate in that loop. What we try to do here is to enable this design platform with machine learning. So we've heard in the previous presentation very nicely as well. The design spaces are very big, and very often, especially in the case of formulations, we can't necessarily approach everything with physics-based simulations. So we here we try to use data that we've derived from physics-based simulation for part of our data set. We label that data for machine learning approaches, learn structure property, mixture property relationships, predict then new structural components or new structural materials. And then we score those. We can go directly to synthesis, or we can revalidate the physics. So that's a kind of process that we are also applying to a formulations case study at the moment. One thing that I'm not going to talk about today, but please contact me if you're interested in more detail. We're also working on active learning loops here to close that loop and really go in iterations where we select that small set of structures, we build these machine learning models, and then we improve them based on our quantities that we need to optimize and where we need to find an optimal parameter set for. And so that's indicated by that dotted line. So that's also something where we're active in these active learning workflows to iterate then through physics-based and machine learning to make sure that the models that we're learning are really capturing the necessary feature spaces. But at the same time, we avoid the necessity to really screen with explicit physics-based simulation on the whole design space. Okay, so what we're working on then has basically 3 pillars, and I'm trying to touch upon each of those a little bit. So physics-based modeling, we've heard a lot about that today already. Things like quantum chemistry, molecular dynamics, etc. What's of course important here is to develop automated workflows to make that easily accessible and then also reproducible. Then machine learning, for example, structure property or mixture property relationships, just to speed up the screening of large chemical spaces. It's not going to be a topic today, but we are also active in deriving de novo design and generative models. So where we really, instead of screening a preset space, the algorithm comes up with new suggestions and tries to optimize that with different procedures. And then one pillar that we also strongly believe that is really necessary to make this kind of digital research successful, especially in a commercial setting, is then what we call here the team-based intelligence and collaborative informatics. So platforms that enable to really the digital and experimental results to be viewed side by side on equal footing, and in a way that is accessible and understandable to both experimental and theoretical scientists. And then also the facilitation of collaboration whenever teams are split across different locations, geographies, different teams, time zones, etc. I think we're all familiar with the challenges of that nowadays. So we really need platforms where we can bring that together. And then also from the modeling perspective, such platforms can provide then also an easy access to well-defined, controlled, reproducible models that have been devised for a certain project and then stay consistent and controlled over the course of a certain project. So I'm going to try to sort of touch upon all of these a little bit. Okay, so high throughput screening, we have over the course of time done different kinds of studies. As an example, I'm bringing here one for polymers, just very briefly as a summary. This was published about a year ago as well. So we did here a molecular dynamics large-scale, high-throughput mega run, where we screened the glass transition temperatures of a bit more than 300 polymers using an automated workflow that we pre-built that takes the different polymer chains or the monomers, built up polymer chains, puts them into simulation box. We have ways of growing the polymers in an entangled way with Monte Carlo-based approaches, relaxing that with molecular dynamics, and then running a cooling protocol to get the density versus temperature plots and extracting then with an automatic fit to that the glass transition temperature. For the study, we used our molecular dynamics engine, Desmond, which is running on GPUs, and our force field, the version that was up to date back then, that was OPLS-3E. We are constantly expanding our atomistic force field to include wider and wider molecule and materials ranges. So here a plot of the results that we get for calculated versus experimental glass transition temperatures. We see a very good ranking, especially of the glass transition temperatures for these polymers. The color code gives a standard deviation of the different evaluations. So because we're running 10 replicates and we're sampling at each point here, we can do quite a bit of statistics and then come up with a standard deviation that gives us a little bit how a measure for how reliable we think based on the simulation the result is. So with that, in this case, in case you're interested, so that was a compute time on a single GPU of about 10 years. For, yeah, with the 10 replicates, that was like more than 3,000 simulations that were run from beginning to end. And then by really parallelizing that and plot resources, we got that simulation down. So that is something that similar studies we've done in different areas. So one goal of the study that we are currently doing, and which I would like to present, is on the one hand to apply our tools to biosurfactants-based formulations, but also to see how we can use the data from these screenings that we do with molecular dynamics in machine learning approaches afterwards, and whether we are able to build a good machine learning models for these formulation-based properties based on our simulated data. And before I begin, I want to say that most of the calculations were run by my colleague Ben Koskia from our simulation science team, and so I'm very grateful for him to run these, and want to give credit to his work here. So biosurfactants, of course, very active area of research as eco-friendly alternatives to formulation ingredients, wide range of application areas, mainly in detergents, soaps, etc. There's of course a high consumer appeal, renewable, biodegradable. They often even have a competitive performance in that they are milder, but still have a comparable performance to existing surfactants. And one bottleneck that has existed is the large-scale production, but it seems with recent biotechnological developments and also different directed methods, and that barrier seems to be at least lowered in recent times, making wider ranges of biosurfactants and also in larger scales available. So basically, some microorganisms need to ferment oils or sugars, and based on those, produce then the biosurfactants. There are different classes of biosurfactants. The one that we are focusing on in this study is rhamnolipids. There are also phosphorolipids, surfactants, and others. But here for the initial study, we are focusing here on rhamnolipids. And there are different design parameters that are available on the experimental side. The lipids can be modulated in tail length, they can be cyclic versus linear setups, there's concentration, mixture, parameters, co-surfactants, salt concentration, solution pH, temperature, etc., etc. So for this initial study, we decided to start with a defined chemical space and also processing mixture space that is summarized here. A reference down here is a review of rhamnolipids that are accessible through known and accessible through biotechnological approaches. And we are focusing here in the design space on anything that is available and described in this paper, but the basic design space with these rhamnolipids, we have a rhamnose unit and a lipid unit, and then there's can be monorhamnose, where there's one rhamnose unit, or dirhamnolipids. We have two rhamnose units, and then similarly we have either monolipids here on the left, or we have dilipids with two lipid units. The design space we went with at first to apply our workflows is varying on the one hand the concentrations, so starting with 5 weight% and going up to 15 weight% in our aqueous solution. The lipid tail length, so we are varying the length of these lipid tails here. And then one effect that is very strong on these formulation properties is typically the pH. So depending whether these are protonated or deprotonated at the acidic unit up here, we get very different properties. So that's another effect we wanted to include right in this initial study. So we are looking at three sort of model setups. One is low pH and fully protonated. Then we are looking at half protonated, so pH equals pKa. And then one fully deprotonated, resembling high pH conditions. The pH or the pKa for these types of systems is somewhere typically between 4 and 5. And from this design space, we chose every type of rhamnolipid that is being described as existing and accessible. So in total, that added up to about 150 total systems. Okay, so our simulation setup, we use here molecular dynamics workflows. You're especially interested into the aggregation behavior and the behavior of these surfactants in aqueous solutions. So with each of these rhamnolipids, we build the molecular structure, and then we place those into a simulation box. We always keep the number of biosurfactants per box constant. So we always have 100 of biosurfactant molecules per simulation box. We chose this because we are primarily interested in the trends in aggregation. To really see, even though the absolute sizes of the aggregates, of course, dependent on the amount of biosurfactant also available in the simulation box, what we especially want to see the trends between the different conditions and biosurfactants. So we kept the number in this case constant at 100, and then filled the simulation box up with water in order to achieve the targeted weight percent. These simulation boxes here, for example, for one of the dirhamno-dilipids, and to have better visualization, the waters are hidden here, so we are only showing the rhamnolipid in the simulation box. And so we first run some equilibration protocols that we apply routinely, a series of some Brownian relaxation, molecular dynamics at low temperature, then going up to high temperature. We equilibrate at constant pressure, constant temperature. And from that equilibration, we sort of average the volume of the simulation box. And then we run a 100 nanosecond simulation at constant volume. And the trajectory that I'm showing here, I hope the video is coming through, that is showing those 100 nanoseconds production run for the molecular dynamics. So I think I need to switch the laser pointer off, yes, to go to different stages here. So in the beginning, we still have smaller aggregates here, and they get a little bit bigger over the simulation time. And then at the end of these 100 nanoseconds, we end up for this concentration and the protonated forms at low pH conditions with a few relatively spherical aggregates in the system. So we're going to stay with this lipid for the moment and increase the weight percentage. So this is an example for 15 weight percent. So if we run this, again, the 100 nanosecond production run to look at the aggregation behavior. So here we see that over the course of these 100 nanoseconds, we have here a more complex aggregate forming. It's sort of a worm-like aggregate at this higher weight percent, still at low pH conditions, so fully protonated. And then at the end of our simulation, we sort of have that worm-like aggregate forming in a quite stable way. Again, because we're keeping the number of biosurfactants constant within the simulation box, the total size and the total shape might sometimes change when we sort of include larger systems. But what we're really interested in is the trends, for example, when going from these low pH conditions to high pH conditions, what does that do with the relative trend? So what does that do with our aggregates? And then if you look at this, oops, wait, let's see. Why can't I play this video? Okay, there it's coming through. So here in this case at high pH, where we have the deprotonated form, the sodium as counter ion, we have electrostatic repulsion between the head groups. And thus we have then, and that's also seen experimentally, when deprotonating, usually that increases the disorder in these systems, and then basically leads to the breaking up of larger structures that have been formed in solution, and leading to more micellar structures instead of these larger, more complex aggregates at low pH. So that's basically, from a qualitative point of view, structural, what we would also expect from experiment for such a series of simulation. So that's already great. And so the next step is then to think about, okay, what kind of observables from experiments, so how can we bridge here between simulation and experiment? What would make sense to look at in our machine learning model to see whether that we can get useful models out of such molecular dynamics lens. So I have here different experimental observables like critical Miser concentration, forming behavior, viscosity, morphology, etc., etc. They correlate with different types of properties that can be derived from modeling. So for example, for critical Miser concentration, forming behavior, the surface tension is a property that can be accessed in simulation and is correlating with them. So surface tension was the next thing we looked at. So we introduced a vacuum space in the simulation box to create an interface between our mixture and vacuum. Equilibrated that again with 50 nanoseconds, and then extracted the surface tension based on the pressure tensor. Here we show some results for this rhamnol dilipid here. So in all the cases, we usually get a aggregation and interface, and then also some of the biosurfactants staying in solution. What we can see here is also with protonated mixed to deprotonated, we see here some trends where with the protonated, we would expect here lower critical Miser concentrations because we have easy aggregation. So for that concentration range, we already have a plateau of the surface tension, while for the deprotonated in green, where we expect a higher critical Miser concentration, here we still see a drop of the surface tension with the weight percent surfactant. So from the trends and the qualitative trends that we want to extract here, so that corresponds to what we would expect for such systems. So that is one thing that we extracted. Then viscosity, we used here our workflow that we've implemented for extracting shear viscosity based on the Green-Kubo integral. So we are integrating the pressure tensor autocorrelation function. For this case here, to obtain the shear viscosity, the plot here on the top left corner is showing the viscosity trend with the weight percent biosurfactant. This is averaging actually over all the systems and all the conditions at 5 weight percents, all pHs, all diamylolipids, and 10 replicates each. And sort of the bars here, they give an indication of the spread of values, but we still, even when averaging over these systems, we see we have a strong trend with the weight percent. And when we zoom in at 15 weight percent, we can look at trends for the pH, and we can then zoom in again. So if we zoom in at high pH, so we zoom in into that data point, then we get sort of the different rhamnolipids at that pH value. So we can analyze that. So that is an analysis we looked into. We didn't look into cloud point itself, but what is important for the cloud point is, of course, the size of the different aggregates in the solution. So we are analyzing those. And what we get is a wide range of different system or of different aggregate sizes, depending on the conditions, the size of the systems, etc. So that is also the radius of gyration is one parameter that we transported further into our machine learning approach. And then the morphology, that's of course also important. Is it more spherical, micelles, or more worm-like aggregates? So here we look at the eccentricity. So how different is it from a spherical shape, or also the ratio of the longest versus the shortest axis. So here we have, for example, a very long axis in one direction and in the other direction, a short one. So that would give us a big ratio here. So we took our molecular dynamics-based screening that we obtained so far for these 150 systems and conditions. We featureize our biosurfactants using molecular descriptors from RDKit and Morgan fingerprints. So in total, it's about 1,000 features. And then we apply here different regression models. We didn't list all of them here, but it's a larger set of different regression models. And then we look at different formulation properties. I have number of clusters and largest cluster as a little bit more detailed example here. So in the top panel, we have from the molecular dynamics, sort of the range of values we're looking into here. So these, how many molecules do we have in the largest aggregate, and how many aggregates do we have in our simulation box? And that averaged over a certain time of the simulation. And then we take these values, we take our design space here, or feature space, and then we come to different models. So depending on the property, different models perform better than others. So in the case of the number of clusters, this XGBoost, so it's a gradient boosting technology, so that performed best, while in the case of the largest cluster, in this case, a random forest was performing best. But we would get very good training and test set R² values on these. And if we look at the whole set of different properties, so then we get here an impression. So we looked in this plot here at the number of clusters, surface tension, largest cluster, radius of gyration, eccentricity, so that's sort of the deviation from the spherical micelle. And this is sort of the one that is weakest in performance. So that's around the test R² around 0.5. That's sort of the ratio of the different axes within the structures. But overall, we are very happy to see these correlations for these properties in general. And we're further continuing to expand this. And just very, very briefly at the end, what does it look like if we want to bring this together and enable this research in a collaborative environment? This is a screenshot from a web page based application called Live Design that we are developing. And what we have in this case is here the data set that's been uploaded by Ben in this case here. We're showing the structures, names, etc., different properties. And then we could have here different preset simulation workflows or upload the data. And so we have here, for example, simulated viscosity, predicted surface tension. This would be a machine learned model that has been uploaded here. So whenever drawing a new structure, making modifications, that we can then, on the one hand, keep track of it, make it available to our different teams working in different locations. Ben is located on the West Coast in the US. And then also have different workflows and machine learned models for such projects in one place to apply them. So that is sort of closing the circle of the different pillars for applying such projects and handling then the data also that come up in these projects. And with that, I'm at the end of my presentation, and I want to thank you for the attention. And are there any questions?
Yeah, thank you. There are already a couple of questions in the chat. Mm-hmm. So let's start with Joanne Cook. She asks how long these simulations take, and she's talking about the rhamnolipid micellation simulations there to get 100 nanoseconds, and were they run on CPUs or GPUs?
Mm-hmm. Oh, that's a wonderful question. So the system size was here between 30,000 and 300,000 atoms per simulation box, depending on the type of lipid and then the weight % concentration. So the total simulation time for running everything for one structure was between 12 hours and 5 days, depending on the system size. And we run those on GPUs.
Okay. The next question is from Alessandro Patti, and the question is, the values of shear viscosity at different pH seem to be within the error bar and difficult to distinguish. Possibly this uncertainty is due to the noise associated to the use of Green-Kubo equations. Have you considered to calculate the shear viscosity with out of equilibrium MD simulations?
Yes, that is something that we are definitely considering. And so they are still averaged also over different rhamnolipids. So the pH dependence was not for one rhamnolipid. So that also creates an additional noise in that specific graph. But that point is very valid, and that is something we are exploring.
And regarding to the pH, there is also a question from Paola Carbone. were these simulations actually run at constant pH simulation? So were these run at constant pH in these simulations? Okay.
Yes, that's sorry, not constant pH, so constant protonation states. So we assume constant protonation states, and we say this is sort of like extremes of the pH, like low pH, high pH, and then exactly at the pH where we assume 50-50. But it's constant protonation state, sorry, yes.
Okay, and yeah, Paula also commented that out of equilibrium simulations might break the microstructure. So maybe something to look out for in the future.
Exactly. So that is definitely something that additional effect that comes in when going to the non-equilibrium one. So we started with the equilibrium here, and but it's a very valid point that we're also exploring.
Yeah, and this brings us then back to the other talks we had today about worm-like micelles rapturing and all that. So I think that's a nice point to close. There are also no more questions in the chat. So thank you, Caroline. Also thank you, Brian, and all the speakers today. And I think with that, I'll hand back to Flor for the wrap up.
Yes, thank you, Stefan. Well, it seems that we have reached the end of this very interesting meeting. We have heard modeling and simulation applications in a wide range of fields, from rockets to detergents to skin penetration models, and we also heard about different tools that are used for these simulations, from physics-based models, atomistic simulations, to applications taking advantage of machine learning for enabling us to reach systems that wouldn't be possible to model from just using physics-based models. I want to thank all the speakers for making this meeting so interesting, for keeping everybody to time, so that was absolutely wonderful, and also all the participants, all of you, for your participations, your questions, and your comments during the meeting. I also want to thank the members of the organizing committee, Jill from the Formulation Science and Technology Group, Charlie from the Statistical Mechanics and Thermodynamics Group, Paula Carbone from CCP5, Stefan Koehler from BASF, and Ana Laura del Regno also from BASF. The recordings for all these talks will be available next week in the Formulation Science and Technology Group website. That is where the program of this meeting is, and all the links that you got in the emails are. So over there, the recordings will be available. I will also send certificates of attendance to everybody who requested them. Don't forget to complete the feedback form. Your comments are very welcome, they're very useful, and they help us improve our future meetings. And also do get in touch with the Formulation Science and Technology Group if you want to suggest a topic for a future meeting, or if you want to get involved in the organization of these meetings or of a particular meeting in the future. And with this, I want to close the meeting. Thank you all for your participation, your hard work, and have a nice afternoon, and we'll see you in the next meeting.